Okay, the numbers seem to have stabilized a little, so maybe we'll get started. Good morning, everyone. This is day 5 of the ICE Plus course. We have a special guest instructor or special instructor, given the time zone difference. Zhang Yunjun is with us today, and he will be leading the first couple of activity sessions with you all. Maybe you'd like to introduce yourself to this crowd.
Yeah. Hi, everyone. Good morning, good evening. I'm right now in Beijing, so I'm right now in Shanghai, so it's a little bit time difference. I'm Zhang Yunjun, a researcher at the Chinese Academy of Sciences. Before I'm joining here, I was a postdoc at Caltech, and before that, I was a PhD student at University of Miami, where I was taking taking this class about 11 years ago. And I have been working with InSAR for a while now, and I'm working mostly on the InSAR 10 series. So today I will go through with you guys on the software that me and Harish primarily developed during our PhD at the University of Miami, and then later was further developed it at the JPL and the Caltech.
Great. We'll look forward to that. I'll just show you briefly what we have on our menu for today. So we have until around 10:30 to discuss results and problems, as we have been doing every day this week. And then we'll hand over to Yunjun at 10:30. And there will be sort of 1.5 sessions on how to set up and run MintPy. And then a session after the break about using MintPy with Opera and Opera displacement products. And finally, we'll hand over to Scott and Sarah, and they will show us how to use Dolphin and how that code is set up and how you run it. And Dolphin, of course, is the code that is used to produce Opera and is the latest and greatest PSDS code that's come out of JPL. So that's what we got lined up for you today. So let's use this time wisely. And does anyone have anything they'd like to ask or like to show from their homeworks or other issues that have arisen? Camilo.
Yeah, how are you? Just like thinking about the exercise that we yesterday of time series for the not time series, but like the velocity of the glacier and using cross correlation methods. Can it be implemented to, for instance, not track displacement, but maybe change? I'm thinking about like some applications for monitoring the growth cities. And I feel I don't know if it will make sense to use something like that to track the difference between one image and a couple others. But the difference will be not displacement, but new buildings and stuff like that.
I don't know if Franz wants to leap in here. There are several things that occur to me that you could do in that space. One would be to look at changes in SAR correlation, which is sort of a byproduct of the interferometric processing. Every time you change the landscape by putting a building in, you'll change the scattering properties of that of those pixels. With adding buildings, typically what will happen is the correlation will get higher compared to what it was before, because buildings are very stable scatterers of radar, as we have seen in the past. So you could potentially look for improvements in SAR correlation, or SAR amplitude, I guess, would also get brighter with buildings. Okay. And yeah, I mean that would be possibly a role for the stack processor in ICE, that you could process a large number of correlation images And I think one of the workflows does that actually in the stack processor. Seda.
Hi, Gert, how are you?
I'm good.
I listened to you this year, and very nice to see you here. I want to ask you a question about that I don't understand very well with GNSS. We reference, for example, European plate or Arabian plate to see the difference in the faults. So, but we don't do this in INSAR, right? We only reference on a point or somewhere, but we don't exactly fix a plate, fix a reference plate. How can we understand the situation in the fault then?
Yunjin, you can answer this.
Yeah.
Is it clear?
A great question. In our field, we did not really consider it that much. Actually, my first time I thought about this was actually a poster from Gareth many years ago in AGU. And nowadays, actually, there's a couple of PhD students at Caltech. They actually published a paper, two papers recently. Actually, one is from Oliver Stephenson, another one is from Wen-Kai Liu. Both work with Mark Simons, and then they showed that with Sentinel-1, we have 250 kilometer swaths, and then you can actually see the impact from the plate motion on INSAR because even if we have a constant velocity, like a horizontal velocity, because of the variation of the instance angle of the loss vector, this constant motion will be projected in the left side as a phase gradient in our velocity, and we have been seeing that actually there have been people from Europe saw that many years ago, and now we have seen that again also, and Ollie and Kai actually confirmed that with Sentinel-1, and then they have developed some code to taking that into account. And later today, I will show you that and their paper. And actually, interesting thing with Kai is that he took it one step further. That like GPS, he used the INSAR velocity to constrain the plate motion for the first time that I know of. And it has been, and the result looks pretty precise.
Thanks. Then can we do this with NISAR? Because we will have a lot of time, I suppose, to get the
Yeah,
data, right?
I would think so.
Okay, thank you.
Yeah.
But maybe there's a more general point about like a referencing of
Right.
star velocities as well.
Right. You want to take more on that?
Yes. Or you. I mean,
Please go ahead.
oh well. So I mean, in general, INSAR velocity fields are not tied to a reference frame in the same way that GNSS ones are. This is something that we really ought to get a stronger handle on in general, but it's a similar situation to if you had a GNSS velocity field and you just held one station constant and measured everything with respect to that. That's the kind of the situation in most INSAR data, that we have a reference point which is set to be zero, held to be zero, and in time series analysis you'll see this with MintPy. We carefully select a reference point location, and that basically is the reference to the whole velocity map that you produce. And that will have a zero velocity, even if, of course, in an absolute reference frame, that location might be moving. And one of the strategies we sometimes use to like give it a bit more of a concrete basis is to choose the location of a GNSS station as the reference point for the the velocity map. And then at least you have some idea of what the how it would relate to a reference frame. And we sometimes do things to align GNSS and InSAR by taking pairs of stations that are within our InSAR coverage and looking at the differential movement between them, which you can project into line of sight, and then you can use that to adjust your InSAR dataset and shift it so that they match. And some of the work that I have done with Simsanga, looking at ARIA data sets that span the whole of California, we have done some kind of alignment with the GNSS stations in each track to try and make the data have a bit more of a stable reference.
And I think with Sentinel-1 and NISAR, these questions are emerging more and more. I think before Sentinel-1 and NISAR, we just had a very strong focus on more localized signals, partly because of the size of the swath, partly because of other data problems we had, like orbit uncertainties and other things that are just were more present and made it really tough for us to look at these very larger scale phenomena. And so for a long time, I think we just considered InSAR as a thing of very smartly interpolating between GPS stations. But now I think we have to think about what a community is thinking more strategically about how do these data sets connect and how do we build like a continental geodesy framework based on all these resources that are available, anything from like satellite geodesy and VLBI to GNSS to InSAR, and how they all connect with each other.
There's a question for you to answer in the chat and the Q&A. It's an ASF related one. I'll take Alaresa's question in the meantime.
Okay, thank you very much, Gareth. So I have a question related to the discussion you had already. So I've seen quite lots of papers for just how to choose the reference area or reference plane. For example, I've seen lots of papers, they have selected several GNSS stations as the reference in order to have a reference plane instead of having a reference point. But my question is a step behind. So why we consider InSAR measurements relative, basically, because I think what we are measuring is reference to exactly to the location of the satellite, as I understood so far. So what is basically the role of the reference point that we consider in the area in order to, I don't know, I've seen lots of papers that they say there is 2 MintPy phase ambiguity when we don't have a reference point and stuff like that. But generally, I haven't yet understood it perfectly. So appreciate it if you could elaborate more on that.
Yeah, Yunjin, do you want to take this one?
It's a very good question and very difficult to answer. If you think about it like GPS, all this is because that we are using interferometry that has the ambiguity or the integer number of 2π, because imagine if one day we have a new technique that does not use interferometry and that does not have that integer ambiguity, then we can directly measure the distance between the SAR and then the ground target. Then we don't have this problem anymore, right? So the whole thing is because the distance between the satellite and the ground is composed of the integer number of 2π plus a fraction of the wavelengths, and we don't know the number of those integer ambiguities and actually in the DEM generation from the bistatic interferometry like TandemX and the Chinese SAR mission Lutan-1, which also does the bistatic interferometry, where there actually has a step to estimate that absolute integer ambiguity and that step is actually not so precise, but sometimes I guess precisely enough for DEM, which is only has meter scale resolution, meter scale precision. And for the future, there is related with this, there is one paper from Xiaohua Xu and David Sandwell, which they published in 2020 in IEEE TGRS. They discussed something about this, but I don't think is right now a fully community consent on this. And I guess in the future we might resolve this. There are many ways to tie InSAR with it, to tie InSAR to other reference frames. GNSS is one, and there's another one from a research from a scientist at Australia where she tied this to the to one, what is that called? I forgot that one. She tied that to one of this another geodesy
VRBI, like a radio telescope.
yeah, right, that one, that paper, yes. So I guess I mean right now I don't think I actually have a very clear answer to your question.
Thank you, Yunjun. But the only concern that I have is that so we always have 2n ambiguity in our measurements, and that's correct. And because of this 2n ambiguity, we always do the phase unwrapping in order to find how many complete cycles has the wavelength passed in order to reach the ground. So basically, what is the role of unwrapping here if we still have 2n ambiguity after doing that? And we have to still just tie our measurements to a reference point in order to just get the absolute values.
Right, but the strength of InSAR really is to measuring the relative displacement of things that you're not just trying to measure the absolute position of things. You're trying to see that this area moved this far, whereas an area 2 kilometers away moved this little bit more, and you have continuous data between those 2 points that shows you very clearly the relative movement between them. Right, so what you're trying to fit, if you're trying to fit a deformation model to InSAR, is you're trying to fit the pattern. You don't care so much about the absolute position or the absolute distance between whatever you're measuring and the satellite. But that is one big difference between GNSS-based methods where you do actually know very precisely in 3-dimensional space where your station is and how far and where it was before. In InSAR, it's very much like you're measuring relative movement. And there is still value in that, even if you don't know how many multiples of 2 pi the ground surface is between from the satellite. But it's because you know that this pixel 3 pixels away is 5 radians further closer to the satellite than this other one, and that still tells you something about how the ground moved, and you can still interpret that and understand the movement of the ground.
And one example with that was the strain and stress, which they usually just do a spatial gradient after the velocity or the deformation we got from InSAR, and in there we basically removed all the impact from the referencing. Back to your exact technical question is we need phase unwrapping because at least after phase unwrapping we used to have, before phase unwrapping we have different integer ambiguity for all different pixels, and after phase unwrapping we supposedly only has one, right? All the pixels are sharing one common integer ambiguity.
Yeah, thank you very much for the elaboration.
Sure.
Milo has his hand up again.
Yeah, just follow it into what Garrett just said. Since then, we are like not measuring, we're like measuring the displacement of one pixel and I guess the other. Should we make something to the final outcome, like the displacement man? I don't know, reducing the mean or something like that. Like since there is no like a reference, can I do something to make the data, I don't know, nicer, more Is there any extra step, or you just go for it to whatever interpretation that you need to do?
I mean,
Like, I don't know,
we've been doing
normalizing the
this for
data or
30
something like
we've
that.
been doing this for 30 years, and we have gained insights into how the surface is moving without the need to have these very, very precise registrations. There's still a lot you can do, especially if your interferogram or your stack or your velocity map covers areas where there's no deformation, where you can be very sure that, you know, it's the ground is stable, and then you sort of transition into an area which is moving. You can see the difference, and you can see the relative motion between two things. Yunjin mentioned strain, and strain is really what breaks things at the surface. So if you have like this, if you have a sort of an engineering mindset and you're trying to see if like subsidence in an area is going to cause problems for infrastructure or something like that, then, you know, the relative motion between 2 points near this deforming feature, the distance between them and the amount of movement that you have will predict a certain amount of strain between them, which, you know, is still like a real legitimate thing that you can interpret and will have physical consequences for the surface. Similarly, if you see a surface rupture in an earthquake, you can measure how far the ground moved either side of the fault, and you have some idea of like what the damage would, what the strain would be on the fault zone itself, where that happened. You can measure the offset, you can measure the displacement. So I don't know where I went with where I'm going with this exactly, but I say there is still a lot you can do without having a very precise referencing of your images to like an absolute reference frame. Although, of course, it would be even better if we had a framework for doing that. And there are, as Yunjin mentioned, several groups that are working towards that as a kind of a goal for InSAR, is to put it in a much more rigorous frame.
And it's not a weakness of the the approach, as long as you understand that it is in a relative measurement. It's not unique in that sense. One of the best tools for measuring height and changes of height in the field is leveling. It's the most precise way of doing it. It beats GNSS by a long shot, and it's inherently a differential measurement. It's very similar to InSAR in that it's really, really good at measuring changes of things in time and space, but really not that great in measuring absolute things. It doesn't mean it doesn't have any validity. In fact, it is the tool to use in the field to come to very precise measurements of variations in height in time and space. So that's what InSAR is really best at. We're getting better, I think, at absolute things as people think more about how to reference to other measurements. GNSS in some ways is not different. It requires other measurement devices such as VLBI to connect its reference frame to a more universal reference frame that's connected to the universe. So we are measuring motions relative to other things. Some of these relative things are bigger than us, so we don't perceive them necessarily as much, but in other ones are at smaller scales. So, you know, in some ways, everything's relative to other things.
And I just want to add one more, is that it's really the two sides of the knife. Interferometry, we have this absolute reference issue because of interferometry, but interferometry is not the only used in InSAR. It's used in microscope, it's used in telescope, it's used in the cosmic imaging. So it is the interferometry that we use that really makes InSAR that can measure this millimeter scale of deformation, while at the same time it brings the phase unwrapping issue and makes the whole absolute referencing a problem. But it's the two sides of the knife, I think.
I think there's a question in the Q&A that is a bit MintPy technical that Yunjin might be able to answer sort of in text. And it might be that later on we cover that anyway.
Relates to the different kind of geometry files you get from Gamma than you get from ISCE.
Yeah.
Yeah.
So I think it is possible to modify that, but I'm not sure if it's how much it would take to do that.
Oh, you have a minute, so if anyone else has a question, this would be a great time to ask it.
Very good conceptual questions today, though. Very interesting.
Yeah, I know.
I would like to thank you all, by the way, for doing this. Thank you.
No problem. Alireza has his hand up again.
Yeah, sorry for the interruption. So I have a question from Yunjun. If we want to process actually several tracks of Sentinel-1 data, we have to use ICE for each track separately, and then MintPy separately, and then we have to do the process, I mean the overlapping areas and referencing them. Yeah, so each tile and each scene must be processed separately. Yeah, am I right?
Yes. Oh, each track anyway.
Each track.
Yes.
It was just for a 1 minute question, so.
That was very, very good, because now you've taken us through to 10:30. And when Yunjun is ready, we can hand over to him.
I would just say it in the word, say it in the voice, Gabriela. It should. If it does not, please open the issue on GitHub. I'll fix it right away.
Awesome. The floor is yours.
Okay.
Ooh, you better pay attention. This is exciting stuff.
So can you see my screen?
Yeah, yes. I see gradients. I guess that's the plate motion thing. Yeah.
Right.
Cool.
Okay. Maybe I think right now it's fine, right?
Yeah, that's good.
Okay. Okay. So today, the last day, we will go with in full force to the time series. And in these two sections, I will show the time series software called MintPy. Its full name is Miami InSAR time series software. It's because both me and Haraj got our PhD at Miami. And this code is open source. It starts with a stack of unwrapped interferograms in both geo or radar coordinate, and it can estimate a time series. And the code is primarily consistent with the products from ICE. However, it also supports interferograms generated from other softwares like Gamma, GMT-SAR, GM, and Snap, and RoyalPack, which is an ancient code, the predecessor of ICE. And the software has a companion paper, which is shown here. And in this paper, it describes all the algorithms and the procedures that is used in the routine workflow of the MintPy software. So if you are interested on that, please feel free to take a look at the paper. And I want to say one last thing is that the code was primarily developed by Hirash and me during our time at the University of Miami, but later words it has been contributed by many people from US, from other countries globally, and right now it's really from my last check on GitHub, it has now I believe over 60 contributors to the code. So that I think that is really what makes it important that everybody could contribute. So please feel free to do so when you find a bug or new features that you want to implement. So today, in the first session, let's go first with the general overview of how MintPy works, and then we will go with a quick time series analysis afterwards. Then come to my favorite session, which is doing the error analysis. That is the signal or noise in our InSAR dataset. So before we go further, let's first run the cells. here, and the second one, which is doing the data downloading. I have already done it, but let me just do a quick let me just delete it, and then so that I can be the same in the same space as yours. I'm here, and if I just delete this one and run it again. So if you run a second cell, it will start to show if you have an issue, then create on your home folder, create a data folder. I think that will fix the issue. Yeah, so it started downloading. So basically we have prepared interference stack from ARIA products using the ARIA tools, which you have used it for in one session on Wednesday, and the exact command that generated this co-registered interference stack is here. So you can later play it yourself if you want it. And this code is right now stored on the AWS, but it's also available on Zenodo. So if you if you don't have access to the Open Science Lab anymore, you can change here to Zenodo, and the whole thing will still works. So so this cell is downloading this cell is downloading the entire interference stack, and is basically the equivalent of the interference workflow that is using the ISCE TOPS stack processing, which is the stacked version or the multiple interference version of the TOPS app. But instead of doing a single pair processing, is doing a smart way of doing the entire SLC stack, so that all the interference will be consistent in space. Oh, why this is not? Oops. This is strange.
Yeah, there's the latest version of Jupyter Notebook that doesn't like HTML figures.
Yeah, if you double click that and just do.
I thought I fixed it.
Oh, you thought yeah.
You need to put an exclamation point in front of the figure,
Yeah,
right?
Okay. Yeah, it's here.
Okay.
Okay, so the routine workflow of MintPy is called the small baseline app. It's like if you think of that, it's like the TOPS app that you have been working through the class. And this routine workflow mainly contains two major steps. One is to do everything in the field domain, which is the blue oval here. And another is doing all the analysis in the displacement, in the time series displacement domain. So what it does is actually is load the stack of unwrapped interferograms, which are consistent in space, load that into one single file, then do a network modification, select a common reference point for all the interferogram, correct some unwrapping errors if there is, and then invert the network of interferograms into a time series. That's what we call the raw phase time series. And after that, everything is done in the time series domain. Basically, we estimate for each state the troposphere, the potential long wavelength ramps, or the DM error contributions. We estimate for each state, and then we form a time series, and then we just subtract that contribution from the raw phase to get a cleaned displacement time series. And after that, we can do more time series analysis by feeding, for example, a suite of time functions to get a more physically meaningful representation of our deformation data. One common thing, of course, is just the average velocity. Okay, I guess everybody is, I'm finishing here. So I guess assuming you are finishing here as well. And so let's go to the next step. The small baseline app, if you just type the -- help, it will show the help message. And you can see it from the help message. It has many steps shown here, similar to the TOPS app. So the whole code is literally running from loading data all the way to the end. and you can run it either like almost exactly like TOPS app. You can specify the start and end step, or you can do a single step with this option. And the configuration or the control of this is just what I said earlier. So the control of this program is through a configuration file, and this is one of the configuration file. Let's just first sorry, let me. Is through the configuration file, which is these two files. So we usually have the default configuration, which has a fixed a file name called small baseline app.cfg file. It contains all the configuration parameters grouped by each steps with default auto values, and all these auto values are defined in the another file here. If you click it, you can see. If you click it, you can see all the detailed values for each of the default configurations. And this configuration file is copied over from the code to the current working directories that you have, and it will read every time when the small baseline app is runs. So this configuration is more for the program itself. And what is recommended is using the custom configuration is optional, but I also recommend it. Is basically a subset of the options that is in the default configuration, and these ones contains the modified parameters that is different from the default values. And this custom configuration is more for the humans, for us, and the names can be very arbitrary. And this fileware has a higher priority than the default template. So if the custom template is specified, the code will update the default value based on these custom configurations. So now let's run the next step. This will write this configuration file into this txt file. It contains a few simple options. The first one is specify the InSAR processor. In this case, we're using ARRA products. And later words, of course, you can try using the ICE, using HYPE from ISF, using GMT-SAR, or using Snap or others. And this basically specifies the path to the unwrapped phase, spatial coherence, the connected component, and all the other geometries, including the DEM, instance angle, azimuth angle, and water mask. And besides that, these are basically all the input of the data. And besides that, we only specify one more options here in the beginning, which is the spatial reference point. So one thing to note is that MintPy is really a time series analysis code. It does not do the InSAR processing, and it requires the input of a stack of interferograms. So when we say stack, we mean all the pixels are aligned in space, shown on the left, and the multiple pairs of interferograms produced by TOPS app. If you run TOPS app multiple times, you will have multiple interferograms, and by default, those multiple interferograms are not a stack, right? If you think about it, different pairs has a different reference date, and each different reference date they are not consistent with each other if you don't do anything special from it. So we need a stack of interferograms, not a pairs of interferograms. And for MintPy, there are quite some example data set that you can try from. If you click the link here, which will take you to the documentation website, we have already prepared many example data from ICE TOPS stack, which is a similar thing to TOPS app, from ARIA, which is what we're using today, from HYPE3, and from GMT-SAR. So you can try this data set. They're all available publicly. If you just copy paste this part and run, you should be able to get a result as shown below. And for each of these InSAR processors, their data structure or their environment are slightly different. And if you're interested, we have a documentation here which shows us what the expected data directory looks like. For ICE2 TOPS stack, it looks like this, with atmosphere correction turned on if you have. And the corresponding, and with this data file generated by ISCE2, the corresponding input for MintPy looks like this. And the same thing we have for the other stack processors as shown here. Okay, so I guess that's basically the beginning part. Now let's just run the real data. If you run the next cell with me. These are load the data into MintPy, and since we already have loaded, we don't need to reload it again, and we can just run the next step. And by loading, and at the end of the load data, the output would be the inputs directory, subdirectory within your work directory, and in there's usually two files. One is called the interference stack, which contains all the interferometric phase, the coherence, and kinetic components. And the second one is the geometry. And they also will copy over the custom and default configurations in these inputs. And the interference stack file is an HDF5 file. It has the following data sets, and you can imagine these three parts. They contains many interferograms, so they are actually a 3D data set with M represents the number of interferograms and the length and the width. And of course, you will have a date with the reference and secondary date for each interferogram. And this drop ifgram is a flag matrix. It's a flag data set. It just indicates whether we want to use this interferogram later words. We will show that. We'll show why this is important later words in the network modification step. Okay, and actually in MintPy, there is a very useful program called info.py. It's like GDAL info, if you're familiar with GDAL. You can use this program to inspect the content of any HDF5 file. And if you run it like this, it will show us that this is the file name, the file type, its coordinate, and the metadata that it contains within this file. And at the end, it will show us how many data, what's the data set that is included in this file. You can run this on any HDF5 files. Similar thing we have for interferogram stack. The metadata will be the same, but at the end, the data set will be different, as shown here. And this is what we have. We have, in this case, 961 interferograms with a size of around 1,000 by 1,000. This just show us with a few more options, you can actually print out the exact reference and secondary date for each of the interferogram. So now we have many data. Let's see how it looks like. It runs the plot network, just show us how the many pairs are formed in space. Let's just see it. So it's calculating so right now the code is calculating the spatial mean of the coherence. What it means? It means it is calculating an average spatial coherence value for each of the interferograms, and plot it like this. The first one is just the perpendicular baseline history, x-axis time, y-axis the perpendicular baseline. So you can see it look like this. But at the end, right now, if we actually have a new data from Sentinel, we will see that the perpendicular baseline is getting bigger because the Sentinel-1A is not doing the object control as much as frequently anymore. And this plot is very useful because it actually shows what? It shows for each bar represents an acquisition, and the blue bar represents the maximum average coherence among all interferograms for this acquisition. And the orange bar represents the minimum average coherence for all interferograms that is involved with this acquisition. So you can see basically from this plot how the coherence situation looks like for each of the acquisition. And you can see basically like this state, and this state, even the maximum coherence is not so high. So there may be something special or some problem with these acquisitions. This one is the network that you saw very frequently. and each dot represents an acquisition or an SRC, and each line represents a pair of interferogram, and the color of the line represents the average coherence of that interferogram. And this plot is what we call the coherence matrix. Both x and y axes are the image number or the image index. So we have here the diagonal line represents interferograms that are formed with the two exact same SRCs, which is not meaningful, right? So that's why we specify a black the dark value here, but all the other off-diagonal grids represents the average value of interferogram. So in here we have in this part the small temporal baseline interferograms plus actually the annual pairs that we specially generated for this data set. The temporal baseline among this part is roughly around 1 year. So after we inspect the data set, let's generate some quality matrix, which are some masks and coherence. This one is literally doing the temporal averaging of all the special coherence. So you can see the coherence, what the coherence look like in this data set. Basically around this part, all these urban areas are very high coherent. These forest regions are very low coherence, and all these part are dark values are water mask, are water that was masked. This one is just the water mask itself, and besides that, we also generate a mask kinetic component file. This file is literally the joint of the kinetic component from all the interferograms. We'll show later why it's useful because we use it in MintPy to select the reference point. Because when we select a reference point, we want the reference point has valid values in all interferograms, right? And did we cover the kinetic component in previous class? Should I explain it, Gareth?
I don't think it would hurt to review.
Okay. So thank you. So the kinetic component is a byproduct, or shows that later words is similar look like this for a single interferogram. It's a byproduct generated by snafu. So it usually has 1, 0, 1, 2, 3, like those labels, and the background 0 value, which means that snafu think the unwrapping result is unreliable. So usually the background value is pretty bad, and then we don't think the unwrapped phase there is valid or reliable. So we use this joint result from all the interferograms to trying to find which pixels has valid unwrapped phase among all interferograms, and that is what we use as a base to choose the reference point from. So the next one is choosing a common reference point so that all the unwrapped phase in the different interferograms are consistent in space. And since the InSAR is relative in space, so actually the reference point is very important, and I always recommend to choose it manually, even though MintPy can choose it for you by default, but usually the default ones here is not very good. This is actually one of the few steps, one of the 2 steps in MintPy that the default ones is not good, and yeah, so I always recommend manually choosing it. For me, usually I first run it with a default one to get a very quick result, and then I rerun the small baseline app by first checking the first result and see where the proper reference point should be, and then specify it and rerun the result. And there are some guidelines to how to select a good reference point based on prior knowledge, and you can find it here in the default configuration files, where these are the 3 guidelines which I think are useful to trying to choose a good reference point. You need the reference point to be in a coherent area. You want the reference point not affected by strong atmospheric turbulence. like the ionospheric strikes, and then you want the reference point to be close, but not within your deformation area, right? And with close elevation as your area of interest. And this can minimize or mitigate the impact of the tropospheric delay. So when we add the reference point, we are actually in reality in the code we just add these few metadata into the code. So that's why it's very fast. And you can see it with import py here. And later words, now we have all the infigram in the consistent in space. We can just do the S-bus inversion or the network inversion to estimate the raw phase time series. This is doing the standard, the classic S-bus small baseline inversion, following the Bernardino paper, and yeah, and it's doing that one by one. Okay, and now since we're waiting, let's see if there's any questions in the chat. Or anyone else has a question, please feel free to type it
Yeah,
in
there
the
were a
chat.
few questions in chat that we ended up addressing. So
Cool, great.
there was one that we're just working on. Gareth responded already, and I'm typing up on sort of how do you actually form your interferogram stack. I think that's
Okay,
we try to provide some guidance in the response, but
great.
it's not an easy subject. It's something you always learn doing.
Yes. So in this step, you can see it spends some time, even though it's not so slow. But if you run a bigger step, a bigger data set, you will find it is actually the most time consuming step in the MintPy analysis. So what you can do in later words is actually first don't turn on the weighting in your first run. Because weighting can make everything pixel-wise and makes the things extra slow. For me, I always turn, so the weighted S-bus is always, to me, from my personal experience, it's only one scenario that I have through the last many years, that one scenario that weighted S-bus is not working. All the rest as weighted inversion is always better than the non-weighted one, but the improvement is not significant. So I always use it at the very end. And all the previous analysis, I need to rerun the dataset and update my configuration. I usually just turn the weighting off. Then the next one is to use the parallel processing, which I will show at the end, that MintPy supports the parallel processing by using the Python module Dask, and it can be very easily turned on, and that will save a lot of time during this step. Okay, we have finished it. And after this step, it will generate a new dataset called time series.h5 file. And again, we can run info py to see how it looks like. All this is the same as before, and then we can see there's a start date and end date with it. The metadata is the same as before, and the dataset itself, it has three datasets. One is a time series. Time series dataset is a 3D one with 189 acquisitions. So that's the dimension of our time series. Plus, it has a perpendicular baseline and the date of the time series. And we can plot it using view or view.py, which is the main visualization code in MintPy. It's basically the same role as the MDX, the py from ISCE, if you are aware of that one.
We
But
haven't
this
shown it because we don't, because people don't have
Right.
access to it on Open Science Lab.
Right. Okay. So this one, you will find that view.py is basically your best friend if you are using MintPy, because you will find the H5 file may be a little bit unfamiliar. View.py and info.py can help you to know all the details that the data set that the file has, and it literally plots everything that MintPy generates except the TXT file. It also plots all the ICE and the GMT SAR generated data files. So, and then if you run the view.py with the help message, you will find that the option is very long. It has very many functionalities, making it really powerful. You can actually generate a publication quality figure from it if you know how to use all those options. So I definitely recommend you to spend some time to get familiar with view.py after the class. So this is how the time series looks like. By default, we choose the first state as a reference in time, and we can see that we have around 200 acquisitions, so the time series looks really long. But as we go later and laterwards, we can see these deformation patterns got stronger and stronger, right? So this shows us the cumulative deformation that we have from InSAR with respect to the first state by default. Laterwards, we can change the reference state. But by default is the first ones. So I have a question for you guys. Please type the answer in the chat. Is why we want to invert a network of this small baseline interferogram to estimate a single reference time series instead of forming the single reference network of interferograms at first place. What it means is in the beginning, if you remember, we have around 1,000 interferograms, which we used to invert or estimate this time series, which only has less than 200 acquisitions, right? Why do we do this a lot of work instead of forming those 200 interferograms directly from SLCs? Could you type your answers in the chat?
I don't think the chat box works. So maybe someone should ask a question in the Q&A and people can add on reply to the Q&A.
Okay, I see.
Yeah, so especially the question about how do you pick the right inversion method? I'm not sure if you have time to address that real quick, because there are different options, of course, that MintPy supports.
Different options of choosing the inversion method.
Yeah, I'm not sure if you see. Do you see the question?
The question is unanswered. You need to just add your answer to the answered question that Christy asked.
Okay.
Oh, yeah. There's an open question too. The second one from the top.
People don't seem to be very good at adding to the question thread, but that's what we want you to do.
Yes. So the question is, when we have different options such as covariance, FIM, or no, what's the consideration to get the choice among them? Oh yeah. So all those options I added is because they are used and peer-reviewed in the publications. For me personally, I only choose two for most of the time, which is either is no or the covariance, because I test all of the four. They are almost in practice they're almost the same. That the weighted inversion does not really give a significant advantage than the non-weighted ones. So it's not so they don't have a significant difference. And but the weighting does. The golden line, the silver lining is that the weighting for me almost never ruin the result. So, and in many cases, it will give us a slight improvement on the result, which is reasonable. So I use the weighting, but I only use it at the very end in my last round of updating the result. And if I choose the weighted inversion, for me personally, I always choose the covariance, because from testing, which you can find the details from the paper that I listed in the beginning of the notebook, I evaluate the performance of all those 4 weighting functions, and looks like the inverse of variance works the best, and it's actually also theoretically the best ones.
There is also a question about water masks, like where do you get them, and does MintPy get it for you?
Yeah, the water mask is not operationally generated from or in the standard workflow of ICE top stack processing. You can generate it using the ICE code. There is a notebook that I wrote, put it on GitHub, that you can that can generate that water mask. I will post that link on the chat. And for me, usually I run ICE stack processing, then I generate a water mask by myself. Then I include that as part of the ICE products and then ingest that into MintPy. There is another repository called MintPy tutorial. If you could see the website, right? That I'm showing.
Yep. Yep, we see it.
Great. So there are some quite useful non-standard tutorials for MintPy, and you can find them here. They mostly are listed here. Actually, the first one is to create a water mask. If you click it, it will take you to the notebook. It was just there are steps to generate it, so you can just follow that. Okay, let's do the last ones. Now we have the time series. The very intuitive thing is to just estimate a linear slope and get an average velocity from it, and that's what we just did. The velocity step, and we can plot it, see how it looks like. So this is.
Did we answer your question that you asked to all of us?
Oh, let me see. I forgot that.
There is a few answers in the Q&A now.
Okay.
Under answered.
Under answered. CR.
I think it's the last answered question, where people started to answer the question you asked out loud.
Right. So yeah, Scott is right.
Well, Scott collected other people's answers.
Oh, okay.
Did I click? I'm just typing off the top of my head.
Uh-huh. So yeah, so the reason is because we want to add more redundancy, right? And the redundancy theoretically also makes the noise less, so we can so we can estimate all the parameters more robustly. More physically meaning ones are that the right the Armored says the shorter baseline interferograms can introduce the phase bias. That is true, and that is a new thing. The traditional ones that we want these form the S-bus network or small baseline network is because the small baseline, the small baseline has less decorrelation, so it has higher coherence. And through the high coherence, we can more easily unwrap the phase and makes the phase observation quality better, right? And if we actually cannot really form, let's say right now with Sentinel-1, we have more than 10 years of data. With the C-band data, we cannot really form a 10-year long single pair interferograms from 2014 to 2025, and that will likely be decorrelated in most of the pixels in most of the places. So we do this because we want everything to be fully connected in the coherent way, and S-bus or small baseline is the way to give us coherence, to give us a coherent path. So I see actually quite some people got almost right? Unwrapping shorter baseline can be much faster to run even if you try to unwrap. Unwrapping shorter interferograms can be faster to run. Not, I mean, yes, but also no, right? Unless the shorter baseline interferograms are more coherent. Actually, it's mostly true. Mostly true. Then the coherent interferograms are faster to run.
I had that as an empirical fact based on the first 2/3.
Okay. So let's move forward. So this is the velocity we got from the current time series analysis. It shows the average deformation velocity for these areas. And this is, since this is the San Francisco Bay Area, we have the San Francisco here. We have San Jose around here or here. And we have Berkeley around here. This line is the famous San Andreas Fault. This is the Hayward Fault. And this line is the Calaveras Fault. So we have the whole San Andreas system shown here in a very tight snapshot. And let's do the plate tectonics. The San Andreas Fault is a right lateral plate boundary, right? Which means the plate on this side is moving. If you see my cursor or mouse, the plate is moving towards this direction, while this side of the plate is moving towards this direction. So that's how the plate is supposed to move. And this data set is a descending Sentinel-1 data set. So the satellite is moving like this and with a right side looking towards here. So anything here, the positive motion or the positive value in MintPy in the velocity means the motion moving towards the satellite. Since the satellite is moving like this and looking like this, so the positive value means motion towards this direction. And in here, we have the reference point right here in the gas green. And the orange here means positive value. So the orange here is moving towards this direction. And the blue value is negative value. It means moving away from the satellite, which is moving towards this direction. So this map shows us a right lateral interseismic deformation, which is consistent with our understanding of the San Andreas Fault San Andreas plate boundary. Ali Reza, yeah, please go ahead.
Yeah, thank you. Just in the config file, I see that you have a coherency threshold in the modified network stage, and also you have another threshold in the inversion stage. I think one of them is for spatial, one of them is for temporal coherence. Can you please elaborate the differences on these two and how temporal coherency is computed?
Yeah. The temporal coherence, I will show that later in the next session. So I'll wait for that. What do you mean is here, right? This is the threshold for the temporal coherence. And
So actually in the main config file, a small baseline app.config, in the second stage, modify network,
oh, yeah.
there's a, let's say, mean coherency. So the default value is 0.85.
Yeah, this one, right? I show okay, let me do it here. It's you mean this file, right? This option.
Exactly.
So this one is for the spatial coherence and it's for the average spatial coherence. And this is what we use to just to modify the network. I will show how we do that laterwards on this specific step. And here at invert network step, there is this minimum temporal coherence, right? This one is calculating a temporal coherence, which is different from the spatial coherence. And we just use that to estimate the quality of the S-bus inversion, which I will. Yeah, let me answer you after that.
Okay, thank you.
Okay. So before we finish this part, let's just see the interpretation of these velocities. And right now we have go through these orange values, these blue values here. And do you see anything weird in this data set, in the current result that you don't find is reasonable or consistent with your knowledge of this area of this data set, geophysically or plate tectonically? Any weird features that you find that is that can be that you don't think is right or weird?
You might need to speak up and unmute yourself because the chat doesn't work. But I can see something, but I know the answer, so that's cheating.
Yeah.
Cheating.
If you follow the fault that is next to the reference point, if you follow
Yeah.
up the way all the way up, there is like a change of phase, like over there. Yeah,
Yeah, here.
that's suspicious. Yeah, I don't know.
Yeah, you're right. You're right. This is weird, right? It's it's that we don't know there's a fault there, and the boundary looks way too straight to be like a real natural thing, a real natural feature, right?
Anybody have a guess what may, if this is not real, what could cause an error like this?
Combining the different what was it called? Different scenes together, maybe.
Yes, you're going to the right direction. What things?
Can it be misregistration error?
It's not a registration error.
Maybe it's a wrapping error. Yeah, unwrapping
Yes.
error.
Yes, Devon, do you say that? Yeah.
Yeah.
And good job. Yes, yes. It's an unwrapping error. We will later will show how it looks like in details, and then how to correct for it. Okay. So yeah, so this is basically the main part of here. And one last thing is, after we have the velocities, we will in the code will also generate actually at the same time velocity standard deviation in the same file here, which looks like this. And then this is actually just the fitting residuals from the linear fitting. We estimate a linear slope from the time series, right, for each pixels, and we can get a fitting residual from that. And this is the velocity that is derived from that fitting residual. So it really just shows how well each pixel is aligned, or how tight it's aligned with that linear line, right? Linear slope. And it's not actually the standard or the well recognized or the well acknowledged uncertainty for velocity. But right now we don't really have a good uncertainty or very well uncertainty parameter in InSAR in velocities, and this actually tells us something about it. We can see some features. This black square is the reference point, and we can see more away from the reference point, the value get bigger and bigger. So this is the impact from the troposphere, because the tropospheric delay is actually a specially correlated component. So the 2 points, the closer the 2 points, the relative tropospheric delay is less. So that's also another reason why we recommend to choose your reference point close to your area of interest. And away from here, you can see another feature here. This is in the valley. What's the name of this valley? San.
Which one? Sorry.
Here.
Oh, yeah, Santa Clara.
Santa
Valley.
Clara, thank you. Santa Clara, the aquifer here, there's a fault here also. Actually, here there's a very famous aquifer with many groundwaters, and here is actually the non-linear deformation from the groundwater pumping. And since it's non-linear, so we cannot really parameterize the well with a simple linear line. So that's why it shows up as a big standard deviation here as well. So yeah, so that's basically the main workflow of the time series analysis. 2 parts. We first estimate we first invert the network of interferograms into a time series. Then we invert the time series, or estimate the velocity from that time series. Basically the 2 steps. And another question here, if you could type your answers in the chat or in the Q&A. What are the potential sources that you think that could increase the uncertainty or bias the velocity estimation? How to ask a question? Could someone type that question? I actually don't know how to do it. Thank you. Yeah, atmosphere, decorrelation. Yes, that's all right. Atmosphere, coherence. I guess you mean decorrelation. Yeah. And what else? The choice of reference point, right? DM error, yes. Phase mapping error, yes. I think that's the most of the common ones. Most common sources. The temporal and spatial decorrelation, yes. Okay, great. Looks like actually you guys are very informed. The time function used, yes. The changing of scattering properties like the moisture, yes. That's the new one, yes. Okay, so I guess you guys actually get it almost all right. Actually, all right, not almost, which is awesome. I think let's take a short break here. And let me see. There's one more question. I will try to. Would it be possible to?
There was an earlier question as well about
Yeah.
the method for estimating the standard deviation.
Amrita's question, and there's a follow-up on the very top of the open questions.
The follow-up question is, the answer is no. There's no way of doing it in ICE.
MintPy produces different methods. Oh yeah, there are 2 ways in MintPy in the time series to velocity script. One is doing the one is just doing the estimate from the fitting residual, which is doing a least square estimation, and then use that fitting residual through a linear error propagation law to propagate that into the velocity. Another is doing the bootstrapping, which is similarly, but in the bootstrap way. From our experience, is actually the bootstrapping result is pretty consistent with the fitting residual approach. So really, not much significant difference. And I still want to be clear, the velocity standard deviation is not really a great measure. It's one measure, but it's not the correct or the accurate measure. Follow-up question, can we generate displacement STD from using ICE? No. Would it be possible for someone to elaborate on why we invert the network of small baseline to estimate single? Right. Actually, you already said the answer. The answer is because if we use a single reference, then you will unavoidably form a long temporal baseline in pherogram, and that long temporal baseline in pherogram can be very decorrelated, and then you will lose all those phase informations if you don't have coherency. And the small baseline pherogram will have small temporal baseline, and that can keep the coherence. So also what we really need is we want INSAR is based on coherence. So if we don't have coherence, we have nothing. So we, through the small baseline app, we form the coherent path that connects all the dots.
Yeah, so there's really two philosophies, if you want, for INSAR time series analysis. One of them is the PS, the persistent scatter approach, which does not necessarily require spatial coherence. It analyzes individual point targets, but it's a different approach to INSAR processing. If you base your analysis on spatially filtered interferograms, that the standard interferogram approach that we've discussed so far, then you need to require short temporal baselines, because now you're relying on distributed targets and they decorrelate with time rather rapidly. So if you would form interferograms with a single reference, most of your interferograms will be decorrelated and your solution will fall apart.
Yeah, and even the PS is forming a single reference network. The PS point that you're choosing is actually what is it called, the permanent scatterers. They are usually those urban buildings, human-made buildings, which are perfect double bounce scatter. So their signal to noise ratio is very strong. The coherence of those single pixels or single scatters are also very strong. So they still has. So in those scatters, even though the temporal baseline is long, the coherence is still very good. Okay, shall we
That
take
makes sense. Thank you.
Sure. So how about let's take a 4 minutes break, 3 minutes break, and we come back at 2:30.
Okay. See you in a bit.
See you.
Do we oh yeah, we have a
Hi everyone, we come back. I love this new music. Yes, I love it. Very funny. So in this section, we'll go to the more fun part on the error analysis to see what's signal and what is noise in the INSAR data set. As many people quote, your signal is my noise. So it's very subjective, depends on what you're interested. In this case, we assume in this class, we are interested more on the deformation. So anything that is not deformation is noise. Let's go back to the basic equation here. This is the observations we have. We have the data file, which is the phase, and it contains the deformation, the atmospheric delays, any errors related with geometry from the orbit, from the DEM, and the tidal processes such as the solid earth tide and ocean tidal loadings, and the rest, which is the X, includes all the other ones. And when we say the X, we mean actually all the phase that does not fulfill the zero phase closure of the interferogram triplet. We mean that if we have 3 SLCs, A, B, C, we can form 3 interferograms, A, B, B, C, and AC, and AB plus BC minus AC sometimes is not equal to 0. And the reason includes the decorrelation noise, some potential phase unwrapping errors, and some processing inconsistency due to filtering and multi-looking. And at the end, the non-closure phase from the short temporal baseline interferogram bias. And some people, you might be curious on this part. Actually, it's very interesting that Piyush Agram, he actually formed two interferograms, AB with SLC AB and B. He co-registered SLC A to B, and he formed interferogram AB, or co-register SLC B to A, and again formed interferogram AB, and the two interferograms, they are actually not perfectly exactly the same. But the difference is actually very simple. It's very, very small. I believe it's less than 0.1 radians. So it's actually negligible, but it is there. But besides these ones, all the rest, all the green ones that are marked, they actually fulfills the zero phase closure assumptions. So in MintPy, we treat these two different colors separately. In the first one, when we do the S-bus inversion, we are actually estimating the phase time series that includes all these components except the last one, because the last ones, especially for decorrelation noise, that is relatively random and then follows the assumption of the least square inversion, and that can be mitigated or improved through the S-bus inversion. So in S-bus inversion, we are only trying to mitigate the impact from this delta phi x, mainly the decorrelation noise. And after we are taking care of this, we can start in the time series domain to separate the atmospheric delay, geometry, and tidal processes from the observations to get a clean deformation time series. So that's the philosophy behind. And the quality of the first step of the S-bus inversion is because the S-bus inversion, we are only targeting the delta X, mainly includes the decorrelation, and we can estimate the quality of this by comparing the observation with the model prediction, right? And the delta phi here is the observation, phi hat here is the model parameter, with A or the design matrix or the Green's function, and with A5, which give us the model prediction from the parameters that we have. So A5 is giving us the reconstructed interferograms from the estimated time series. And we compare this reconstructed interferogram with the observed interferogram, and then trying to use this part to normalize these differences into 0 and 1. So when the temporal coherence here is close to 1, it means the reconstructed interferogram is very similar or close to the observed ones. If it's close to 0, that means they are very different. So we can use this to evaluate the quality of the S-bus inversion and use it as a threshold to identify and exclude those unreliable pixels. And that is what we did. So interesting here is this is the temporal coherence we have from our current S-bus inversion. This is the average spatial coherence we got from all those interferograms. And we can see the two of them are very much consistent with each other, right? When the coherence here is high, the coherence here is high as well, except this line, which previously we identified there's potential unwrapping errors here, and we can see in here there's a line in temporal coherence, while in the spatial coherence we don't see it. So which means in temporal coherence we can identify potential phase unwrapping errors, which is a really useful thing. So now since we have seen this equation of how to calculate the temporal coherence, one question for you guys is, for a network with of interferogram with only one interferogram between each acquisition and the subsequent acquisition, or basically a sequential network with a connection of 1. How would the temporal coherence looks like? What would be the value of the temporal coherence if we invert a network of interferograms where the network only has 1 sequential connections? Okay, so Armrit says 1. What others? What's your value? Very high, same as spatial coherence. So this is the tricky thing, right? If there's no phase unwrapping error, then it should be very high, like here. But if there's decorrelation here, it'll be in this here. There's vegetations in the mountains, and the temporal coherence is low. And in here, if we have a network with a sequential connection of 1, the temporal coherence value here will be actually 1 because there's no redundancy there. Then the estimation of the time series will be there's no redundancy, so we are solving the equations with exact solutions. Then the reconstruction will be exactly the same as the observations, right? So basically, in that case, all the pixels will have exact temporal coherence value of 1. You can actually try it yourself. It's pretty interesting, and this means this means the intuitive impression of this is that the temporal coherence is showing us the consistency of among all the unwrapped phase. They should follow the phase closure. They should follow the 0 phase closure of the interferogram triplets, but in reality it doesn't. And the reason is what we just said earlier here. These few reasons, right? And we can only see it if we have redundancy because these ones are random, and we can only see it if we have redundancy. And that's so, which means that if we don't have redundancy when we do an S-bus inversion, then the temporal coherence is not useful anymore. We cannot trust it. Berardino inversion did not use the temporal coherence. This equation was first proposed by Antonio Pepi in their 2006 paper. You can find it here. Okay, so we now know there's an unwrapping error here. Let's see how we can correct it. To correct the unwrapping error, we need to know what it is, right? Unwrapping error literally means the errors added during the phase unwrapping, and phase unwrapping only adds multiple integer numbers of 2π into the phase. So the unwrapping error is also the wrong integer number of 2π that is added during the phase unwrapping. So how it looks like this. We plot a subset of the unwrapped phase during our data set, and we can see all these few interferograms that look relatively normal except these two. And these two, there's a very clear jump, and you can see the value here from -10 to 10. So in here, this is almost 0 to here about is about 12 or something. So that's actually 4π. In here is from 0 to about 6, so that's actually a 2π phase jump. And this phase jump is the clear unwrapping error that is added during the phase stitching process when we trying to stitch multiple frames from one track to form a continuous track. This is how just a special thing of how area products are generated and used. If you, of course, and in this specific case, if you process a long track with multiple frames together in ISCE, you won't get it. This is just basically just an imperfect phase stitching during the area processing. But of course, you could have other potential phase unwrapping errors not from phase stitching. For example, in here, there's an island here, there's an island here. These two also have some phase unwrapping errors. You can imagine there's not really much spatial deformation in these two islands, and their actual value should be a green like the nearby land. So yeah, so we know the phase mapping errors are the integer number of 2π, and it breaks the phase closure. So we can actually use this information to learn more about it. So what we did is we calculate this closure phase, which is the Cijk here from the IJK3 SRCs, and then we can use the second equation to remove the non-integer part of it. So from here, we can estimate the integer ambiguity of the closure phase. And then we can count among all the interferogram triplets, how many triplets are not closed in the integer part. And we can plot this as a 2D matrix. And this is what is done during this step. Amrit asks, is it always possible to correct for phase sampling errors? Okay, Iris is typing.
I was just saying, not always.
Yeah, not always. Let me show you one more example. There's basically the information here. Let me just wait for the figure to come up. Okay, so these are the result of this step. It calculates the t-int value, or what I call the integer ambiguity of the closure phase. And you can see that it actually looks in a similar pattern like the temporal coherence. We still see the clear line here, and the white square is the reference point. So this value actually shows the distribution of RP errors, or the perfect zero value here. So this is the t-int, and the right is the histogram of the left. So you can see here among these dark blue areas, they are almost zero values, which means all the interferogram triplets are closed in the integer part for these pixels. That means they should not have much RPM errors. While in here, the light blue has RPM has about 200 of interferogram triplets that are not closed in the integer part, which means these areas has potentially RPM errors, right? And you can see this part in the peak on the right, and the red and all the rest where the t-int values are relatively random, and you can see the distribution are mainly following the rest part of the histogram. So we can actually usually have three take-home message from this t-int map is that first, all the pixels that has t-int value that is larger than 1, that means at least there's one interferogram triplets that are not closed in each part, which means there's RP errors. So t-int value equals to 1, which means they likely not have RP error there. For this part, where in the light blue region, like these ones, they are RP errors because the value is not equal to 1, but their values are the same, right? They are coherent. These regions are usually internally, they are consistent, or internally there's no phase RP errors, but with respect to this point, there's an RP errors, because RP error is also relative in InSAR. So this is what I usually call the coherent phase RP errors, and they can be corrected using some method. And the rest, which are relatively random here, those random RP errors are usually caused by random decorrelation noise, and they are very difficult to correct for. Okay, so another question is for you guys is, after time series inversion, which metric better represents the quality of the inversion? I want you to please type your answers in the Q&A. A, average spatial coherence, which you have seen. B, the temporal coherence. C, the common mask from the kinetic component. And D, the water mask. This is the most important question that I personally has for this section. Okay, temporal coherence, B. Great. I think my goal finished today. Yeah, so temporal coherence is our best friend after S-path inversion. We want always to inspect that to make sure their pattern are consistent with the average spatial coherence, so that we know there's no RMP errors in our data set, because RMP errors are huge, right? They're multiple number 2 pi is really huge, and that will really bias our deformation estimation. Okay, so and you can see also this figure is actually a very useful figure to evaluate your situation on the RMP errors. Okay, so now we know there's RMP errors, we can how to correct it. There are actually basically 2 methods or 3 methods in MintPy that's implemented. One is called bridging. It's an Asian method, already exists a long time in the InSAR community. Basically by adding the 2 regions with a bridge, and then make sure the endpoints, the 2 endpoints at the 2 sides of the bridge, the phase difference is within -pi to pi. And basically by using a bridge to try to connect all these regions. And you can imagine you can actually build some bridges to connect those coherent phase RP errors, right? And that is what exactly it is doing in MintPy. It add one more ingredient just is to automate the construction of the bridges using some signal processing or the networking things, like use the minimum spanning tree to trying to automatically generate bridges to connect all the regions, and these regions are identified using the using the kinetic component. And the bridging is trying to use the constraints of the RP errors in space, and we can use the similarly use constraints in time because of the phase closure thing, right? And then we know phase RP errors will break the closure phase, and then we can add a constraint to make the closure phase close. And that's basically the idea of that. The detailed equations is lined up in our paper. If you want, please take a look at that paper, and we also evaluated the performance of this few method statistically, so you can see the how when you should use it. I want to add that the phase RP error is usually big, and you should want to check and correct for it, but the current method is not always working, so you should definitely check your result. If you turn these options on, it's turned off by default. If you turn it on, please check your results after this step to make sure it's really doing correct. It's really doing the correction correctly. So now, if we want to turn on this option, we just add one more option and then write it into the configuration. Write it into the configuration file and then run it using small baseline app. And you can do the same thing for all the options in MintPy for all the options in small baseline app. Okay, so now you can see it's doing the corrections in interferogram by interferogram. It's using the kinetic component here because okay, I will later show you how the kinetic component looks like after this finished. Let's see some questions. So Xiyuan Liu asked, are the phase RP errors always manifested as large-scale patterns, or they can occur only on some islands or isolated pixels? Both. It depends on the coherent ones are usually large scale patterns, the decorrelation, the real problem of the decorrelation is actually not a real problem, right? Because decorrelation are you can see actually the phase from the decorrelation is actually not that big, because the maximum decorrelation phase can be just within minus pi to pi, right? So it's still smaller. The maximum phase error from decorrelation is still smaller than the unwrapping errors, than the smallest unwrapping errors. So decorrelation noise itself is actually not the real problem, but the decorrelation what makes the unwrapping very unreliable. It is the unwrapping error caused by the decorrelation that really make it problematic. So those unwrapping errors from decorrelation, they usually look like random, but unwrapping errors from others that are not because of decorrelation, because for example, because of the indirect decorrelation. I mean, for two islands, they are separated by rivers, by water bodies, by mountains. They can be coherent on the two sides, and then they can sometimes be corrected. How dense does a network needs to be used to use phase closure? Okay, Gareth is answering that.
No, you're answering that.
At a minimum of 2, you need a triplet, interferogram triplet, to get a closure phase, to get a phase closure. So a minimum of 2, but if you see my paper, it shows statistically a denser network is better. Usually, I personally always use a connection of 5 or more, just based on experience. That will give us many interferogram triplets, so that I can have a good T-in value, and also for later work, for earlier when we do the network modification, we have more space to exclude bad interferograms or low coherent interferograms. So for me, generally, general rule of thumb is I generate as much interferograms as I can, supported by my supported by my hardware computing facility, so that I can have more space to play in the time series analysis part. It's a lower limit on a special extent that can be effectively used.
Oh, lower limit. I didn't see the lower. Yes. It's a lower limit on the spatial extent that can be used. I guess you're mostly a lower limit on the spatial extent. Like, what is the smallest region? Is that the question?
Yes.
Okay. I think it's more limited maybe by the resolution of your sensor, what's sort of the smallest phenomena you can study. Lots of people use SPICE to look at landslides, very localized features. And in some ways, that's easier. You can place a reference point very close to the site. And the closer your reference point is, the more you can cancel out atmospheric delays. So you don't have to worry about those so much. And in many cases, say if you have a deforming area embedded in otherwise decorrelated space, it might be good to cut down your area to include mostly the area that you actually worried about. Partly also from all the help that sort of MintPy provides to you. It calculates these coherence metrics and all that kind of stuff, and covariance matrices. And if the area of interest that you're concerned about is reasonably small compared to the extent of the scene, then these metrics may not be representative for your area. So if you can sort of cull it down to the relevant scene, then these like scene-wide metrics that MintPy provides to auto remove interferograms, etc., might then be more representative for the area that you're actually choosing. Not sure if.
Okay. Then can we just take the affected area only? Like, for example, landslide, in case of landslide.
Yeah, if your goal is localized, I think you can focus on that scene, place a reference point close by, just not on the landslide, of course, itself. So you need some area outside of the moving terrain to be able to form a reference. But otherwise, that's what I would do. There's no huge point in processing large areas that you aren't really interested in.
Ali Reza has his hand up.
Yeah, sorry for the interruption. Yunjun, I studied a paper last month. I sent the link now in the chat, so might be useful. There was a new way of, let's say, removing the actually bad interferograms in the network. So it is using only the interferogram between A and B and B and A. So it's I found it quite interesting. So might be useful.
Cool, thank you. I will take a look. Okay, so let's move on. This is how the correction looks like. We plot the interferograms before the bridging, after the bridging, and the kinetic component that is used during the bridging. And you can see the kinetic component here. We basically have two values, which can nicely show us the separation. So really, you can see that the kinetic component can show us the potential phase unwrapping errors we have, which is really, really useful. And one thing is the kinetic component does not is a conservative metric. What I mean is that if you have a kinetic component, then if you have two pixels that has different kinetic component value, which usually means as a potential RP errors between them, and if they are having the same value or within the same kinetic component, which SNAF thinks the unwrapping there is relatively reliable and is unlikely to have phase unwrapping errors. But there are some in practice, there are some parameters to tune to generate the kinetic component, and yeah, and actually there's a paper from Talib Oliver Cabrera. He is a scientist at JPL. He wrote a paper previous couple of years ago on the wetland in Louisiana, using the UAV SAR dataset where the resolution is really high, and you can see the wetland and the leaves or the rivers between the channels that is connecting them by tuning the parameters for the kinetic component. You can really generate a really nicely a map that shows us where the potential phase unwrapping error is, and this is what MintPy is used to guide us to trying to how to bridge all those potential unwrapping errors. And this kinetic component is only available in SNAFU and ICU. That is available. That is another algorithm for phase unwrapping in ISCE as well. And if you're using Gamma, actually, you don't have this kinetic component. So that means you cannot use this closure, this unwrapping error correction methods in MintPy. Okay, after we correct for unwrapping errors, we can modify the network. When we do that, what we really want is actually to modify or drop those interferograms that still has unwrapping errors after the corrections, because unwrapping errors are the bias or the big errors that is in our S-bus inversion, right? And we want them out. And if we cannot correct them, we just drop them. And this is actually a thing that is in practice really important can improve your results significantly, even though it sounds really simple, by just dropping those bad interferograms. And this is showing one example where it's using an LS1 interferogram stack from on Galapagos. This is the Isabella Island, and here is Sierra Negra. This is Sierra Azul, two active volcanoes. This one is inflating crazy, erupted multiple times in the last 20 years already. And we can see that in this plot, the line shows the average coherence, and we can see that all those long temporal baseline interferograms, they have really bad coherence at this region. These lines only shows the average value at this within this blue box. You can specify that in your configuration file as well. And by simply remove all those red lines or those low coherent interferograms within this, and then you can do the exact same S-bus inversion, and you can get a temporal coherence that is so much better within this creator. And these are the masks or the reliable pixel mask from the temporal coherence. You can see previously we lost many pixels within the exact target of our interest, and now we get them all. So this is in practice a really important thing. Another note is in practice in MintPy, when we modify the network, the code is actually not really physically remove them. Instead, we are actually just flip a value. There's a flag matrix called the drop fgram in the H5 file. So we just turn the value from true to false, and of that, which means you can regret your choice. You can redo it. You can remodify your network as many as you want, and it will always work. So you can just really update your criteria of how to choose the coherent good interferograms for your inversion. The next one is the weighted network inversion. We already covered that in the previous round on the questions. Besides the weighting, there's actually a masking which is sometimes useful. When we do masking here, is actually similar like dropping the network, but on the pixel level. We can use for each pixel, right? It's a 3D matrix for each pixel and each interferogram. We have the coherence value, we have the kinetic component, and we can use that to mask out those pixels. And if you do that, then it means then it will bring up a situation where different pixels where we may have different number of interferograms that is inverted for. So in that case, you need to be careful, and that is what this minimum redundancy comes in. Sometimes if you use that, and then some pixels, they have a few more than one SRCs that all the interferograms involved with this SRC at this pixel is maxed out. Then you cannot really estimate a valid time series, a full time series out of this pixel anymore. Then those pixels will be set to none. So that's just the technical details. The important thing with this step is the coherence. That we talked about it, and so we use we use temporal coherence as a threshold to choose the reliable pixels, and by default we choose the value of 0.7. And of course, we also exclude those pixels in the layout and the shadow masks, which is automatically generated by ISCE. And same as the Brandino paper, you can actually perform the least square inversion by minimizing the phase, or you can actually minimizing the phase velocity, which is the temporal derivative of the phase, as the matrix B in the Brandino paper, and that can be specified in this option. Okay, now previously we have corrected for the unwrapping error. So now we can rerun the inverted network and to see how the time series looks like. Okay, it's running. Maybe take a minute or two. Let's see if there's some questions. Okay, all answered. So now I will explain more what we're doing next. With this, we can basically see the impact of the RPN errors or of the RPN error correction in our time series. And then laterwards, we want, of course, not just RPN errors, right? We have tropospheric delays, and we have other things. And the MintPy, the more and more powerful thing in MintPy is we have implemented and are still growing many error corrections or error analysis algorithms, functionalities in the code. We'll show that right away. Okay, it's finished. Now we have finished S-bus inversion, so we will get a new time series, a new temporal coherence. These are the new ones. These are the old ones. So these are the ones without RPN error correction. These are the ones with RPN error corrections. We can see the line here in the temporal coherence disappeared afterwards, which means the RPN error got successfully removed. Okay, so now we have a reliable S-bus inversion. So we got a reliable raw phase time series, and we want to get rid of the atmospheric delays and all those things. And all those things, there are many papers published, and we have many of them are supported in MintPy already. And this just showing us we're not going to run the code here. We're just showing you the functionalities that is supported in MintPy currently. For tropospheric delay, we support the global atmospheric models using PyAPS, a code developed by Romain Julivent and Piyush Agrin at Caltech. And the code is here. So we are actually calling the modules from PyAPS. There's another one called Geckos, which is developed by Zheng Hong Li's group. Used to be in Newcastle in UK, now in Shanghai University in China. This is an online service which has shown some pretty impressive correction results as well. Another one is in the empirical relationship between the tropospheric delay and topography, and that is many times useful, especially in the small areas. I believe in the large areas, it's getting more complicated. Here shows the example from Romain's paper, where this is the dry, where this is the wet, this is in kilograms. These are the predictions from the atmospheric models. These are the dry delays and these are the wet delays. The two of them add together is this one. And you can see these two, they are pretty similar to each other, which means the interferograms we have here, usually the majority of them are actually troposphere, not deformation. So actually we need to be really careful if you are trying to interpret an interferogram without any tropospheric corrections. You can specify all those using the option called here. And after that, we'll generate a new file called by adding a suffix into the file names. So you can so that's basically the naming convention in MintPy. With an underscore, it means we are adding another layer or an operation on top of the previous ones. So in this case, we applied the ERA5 correction to the previous time series.h5 file, and we get a new file. These are the tropospheric corrected time series. Note that PyAPS correction is actually one of our homework. You need a separate account for that, and the details can be found in the PyAPS code on GitHub. You can also correct for ionospheric delay using the split spectrum method or the result coming from the ISCE itself. And currently, all the 3 stack processors in ISCE has ionospheric corrections. These are the corresponding papers. If you're interested in the details, all of them are similarly in a simple ways doing the range split spectrum by split the SLCs in the range directions into those 2 subband SLCs and then form the interferometry between them. This is based on the idea that the ionosphere is a dispersive medium, which means the same ionosphere will have a different contribution of phase if the frequency is different. And based on that, we can use 2 different frequency to to observe the same ionosphere and use that to get how the ionosphere itself looks like. And this is the figure from Heresh's paper, which is implemented in the strip map stack. And this is how it looks like. And when we say the ionosphere is dispersive, you can see the figure here. This is just the actually a simulation with the same ionosphere, and it shows up as in X-band like this, and in L-band it looks much, much worse. So which means if you are processing ALOS, ALOS 1, ALOS 2, ALOS 4, and the NISAR in the future, you definitely want to pay attention to ionosphere. And MintPy does not really do the space spectrum for you. MintPy is just loading the anospheric correction results, anospheric estimation results from ISCE and doing the S-bus inversion to get an anospheric delay time series, and so that you can do a subtraction to correct for your time series. Another one is the solid earth type, which is not really, which is relatively new. Solid earth type, actually from my memory, I just first again saw it from Gary's poster on AGU many years ago. Then Xiaohua Xu and David Sandwell showed this in the paper for the first time in my memory, if I note it correctly. That shows the solid earth type can introduce a long phase ramp in the InSAR as well. And this is how it looks like. And the solid earth tide is actually a well-studied phenomenon. It has a very standard conventions as shown here. This IERS 2010, and there's a new one coming. It really is just the deformation of the Earth's surface due to the gravity pull between the sun and the moon, and actually the majority is from the moon. This is the deformation of a single pixel at Los Angeles from the solid earth tide, the vertical component. You can see that it's actually very high frequency. And in InSAR, we will do a cross sampling of this, and this will introduce a long spatial wavelengths as shown here. So we can see actually this is the relatively realistic ones. The solid earth tide will give us a really smooth, large spatial phase gradient, and but the magnitude here is actually, even though the magnitude here is large, but the area is really large. So actually the if you're looking at a small area, the contribution is actually really, really small. But again, if you want, you can correct for it. It's important if you're doing the large area processings, and it can be done using a new code called PySolid, which I developed, and it can be turned on using this option. The next one is the plate motion, which is what we talked many times today already. InSAR this is the interesting one. InSAR has a reference, even though there's unwrapping errors, even though there's phase unwrapping, there's those initial ambiguities, but even without that, InSAR has its own reference frame, right? And that reference frame should come from the reference frame of our orbit data that we're using. And for example, for Sentinel-1, the orbit is using the reference frame of ITRF 2014. And in this ITRF 2014, the plate is moving. The plate is not static, as shown in these two figures here. So the plate is moving, which means in the InSAR's view, actually, in this case, this is your Asia plate. Your Asia plate is moving. That will give us, because this, even though it's constant, a rigid plate motion, this constant plate motion will be projected into a line of sight with varying instance angle from the near field, from the near range to the far range. So that will give us a ramp, right? And this is how the ramp looks like. Ollie Stephenson showed this very nicely in his paper, that if with the Sentinel-1 we have a so large swath, we can actually see this phenomenon really clearly. And this is how it looks like. With the Eurasia plate, you can have actually a phase ramp of about 3 millimeters per year with one Sentinel-1 track. And if you mosaic multiple Sentinel-1 tracks together from left to right, you imagine the ramp would be really huge. Similar things for the Arabia plate, and so This is really interesting, and but the good thing is that this impact seems to can be easily counted for relatively well using the existing plate motion models, such as the ITRF 2014 plate motion model, which is described in the Artemimis paper. And Yuan Kai Liu and Ollie Stephenson, both were graduate students at Caltech. They have developed the code to use existing plate motion models to correct for these artifacts or these effects. Sorry, not an artifact, effects. And then it's already in a code available called plate motion in MintPy, and you can run that to correct for these effects. This one is currently not integrated into the small basin app yet. We are still working on that. Kai is graduating, so he's actually relatively busy right now. But actually, on the other way around, the plate motion can introduce the long wavelength ramp in InSAR, which we think is a noise. But actually, we can use this to invert or constrain the plate motion the other way around, right? And Kai showed this in his new paper recently. And this is the 3 Sentinel-1 tracks at Eurasia at Arabia Plate around here. And he actually used around 9 tracks spanning the boundaries of the Arabia Plate, and then used this ramp to estimate or to constrain the rotating parameters of the plate, which is an Euler pole. And this is how the plate looked like that he estimated using the InSAR data. And this is the corrections after removing the estimation of the contribution estimation from the plate. So you can see that actually he showed that the estimation from InSAR is actually pretty good. It's not as good as the precise GNSS yet, but it's in the same level. And by combining InSAR and GNSS, you can actually get even more precise estimation of the plate rotation, which is really cool. And I believe the next generation of the ITRF of the plate motion model should definitely start to integrate or thinking about integrating InSAR into these fundamental models that I've been using. The next one is the closure phase bias, which is again the phase closure, but in this case we are more concerned or interested in this non-integer part. The phase closure is the unwrapping error is about the integer part, and the closure phase bias is about the non-integer part. It has been shown to introduce bias in the displacement time series. Firstly, by the teams DLR from Francesco Design and Homa Ansari. And this bias has been confirmed in many studies. Yujie Zheng, she was a postdoc at Caltech, now an assistant professor at UT Austin. She has proposed a simple model that can explain this closure phase and the observed bias, and showing that this closure phase can be an indicator of those temporarily inconsistent physical processes, and one of that can be the soil moisture change. And this is her result, that these are the standard S-bars with different redundancy. You can see the velocity is actually different if you have a different redundancy in this case. This is a southern part of California where this is a dried salt lake. And this part, the green areas here are the farmland. So she processed this data set and with the standard S-bars, and then using her method, she estimated the bias from this processing, and you can then correct this bias for each of them. And then after correction, you can see that no matter what redundancy you are using, you can actually get a consistent velocity with it, confirming the effectiveness of her method. And she also implemented her algorithms into MintPy as a standalone script called closure phase bias. You can run it yourself. Yujie has wrote a long tutorial in Jupyter Notebook with a link here. You can click here to check the details. And the core idea of a correction method is use this sequential closure phase. We're not dealing with 3 in a filigree triplet anymore. We're dealing with longer ones. For example, we can have 1, 2 plus 2, 3 plus 3, 4 plus 4, 5, and then minus 1, 5. We can use this as a sequential closure phase, and based on the observation, based on the experience, that this long temporal baseline in filigree has less bias than the short temporal baselines. So this long sequential closure phase has less bias than the short ones, and we can use the long sequential closure phase as a reference to estimate the closure phase time series. That's basically the simple idea, and you can run it using this script, and we can just show you briefly. One thing is you can use this script to estimate the closure phase time series. Another is you can use it to generate a mask that identifies potential closure phase bias. And this is what we're doing right now because of the constraint of the time. Okay, so this is how it looks like. It's basically the code is basically generating this, what we call the average complex closure phase. The amplitude of it looks like this. The phase part looks like it, and we're basically saying that UJ is basically saying that when we have a low amplitude value of this average closure phase and the high non-zero value on the phase part, then you will potentially has more closure phase bias, and you can generate a map like a mask like this, and you can see this mask has actually is pretty widespread, right? And especially in this region, this is a forest park in the southern part of San Francisco. So basically just saying that if you're actually working on areas with vegetations or with wet soils, you might want to really pay attention to your deformation estimation from SBAS. It can be biased. But again, from what we know so far, this closure phase bias, the bias is not huge. It is there, but it's not huge. Again, then moving forward, you can estimate a ramp and remove it. You can correct for DM error and remove it. And if you done all that and you realize the still and the current method is still not good enough, then there's nothing you cannot really do, right? So in that case, there's one not so good way, but way that is one way is to just identify those bad acquisitions and drop them before you do further analysis. And this is one way to do that by using this residual RMS by basically calculating the residual phase, which are the phase that cannot be corrected for or modeled for using a suite of time functions. Then you calculate RMS value for each of the acquisition, and you can plot them look like this. And then you can use a standard outlier detection algorithm to identify those noisy acquisitions before you estimate a velocity or more complex time functions. And these are the result of that. You can before and with or without excluding those noisy acquisitions. And by doing that, this is also another simple way to find the noisy acquisitions and the clean acquisitions. This plot is some issues with this. Okay, it's just a single plot. Let's forget about this. It's basically generating this plot, and this plot, these are the noisy date, and this red one, these orange ones are actually the clean dates, which means a date similar like this one. You can see it's relatively clean. It means that does not really has much tropospheric turbulence that is remained after after the tropospheric correction, and you can use that as a reference date. So you can use that to change your reference in time. And note that this change in reference is not really it's not really changing any data itself. It's just moving. If you think about a 1 pixel, it's a 1 pixel time series. It's really shifting the entire time series up and down, right? So that's what changing the reference date really means. It does not really affects the velocity estimation from your time series. Okay, now we can re-estimate the velocity. Again, so far, even though I just shown that we have many error correction method, we do not really do them. What we really do is only the RPM error in the very beginning, right? And we can see now compare the two velocities. This is basically before all the corrections. This is after the corrections. Which what we mean here is only the, in this case, only the phase RPM errors. And we can see now we used to have these lines here. We don't have it anymore. So they are gone. And we can plot a profile across this Hayward fault, and we can see a very beautiful conjunction shape from the interseismic deformation across in the fault here. And if you want, you can, of course, since you can see here, we did not use any GNSS here. So our InSAR result is actually independent from GNSS, which means we can use GNSS independently to evaluate or confirm the correctness of InSAR, even though you don't really need to these days, because InSAR has been already well established and well acknowledged as a precise deformation estimation method technique. But anyway, you can still plot it and see how they are consistent with each other. MintPy can, using the view.py, to automatically download the GNSS time series for you. This is a work from me and then also from Rob Zinke from JPL. He extended the support to extended support from the University of Nevada to the side shields from JPL and the ISCE, which is a solution developed by JPL and SOPAC from Scripps. So you can actually specify by adding this option, the code is automatically searching all the co-located GNSS available on UNR by default, and you can see that it's searching this over 20,000 GNSS and find that there's around 70 of them are co-located in both space and time with our InSAR data, and it's downloading them one by one, and it's projecting the 3D GNSS into the radar lamp side, and then it's doing the same spatial referencing with InSAR, so then they are now in the same comparable manner, and they look like this. And we can see the color, the GNSS is shown in the circle here. They are color coded by the GNSS line of sight velocities. So you can see they are actually, the two of them are pretty consistent with each other, except there's few places around here and around here, and I believe there are some reasons before that. For the reason, you can actually check the Nevada website to see each of the GNSS stations to see what is going on there, which is really impressive. With that, you can also plot the diagonal plots, comparing InSAR and GNSS. You can see they lined up with each other pretty nicely. So yeah, so that's basically the second part. Before the end, I want to show very briefly there are some other functionalities which I think is really useful in MintPy that you may want to know of. One is the time function estimation. So far we get the time series, then we estimate a simple linear velocity, but you can estimate more complex ones, right? Like a step function for the co-seismic deformation, the logarithm or the exponential for the post-seismic deformation. All those are implemented and supported in MintPy as well. And you can find the details from Eric Hetland's paper from 2012. This is many of them are already supported in MintPy, as shown here. So you can do a more complex time function estimation. In this case, oh, I now know why. I forgot to run this step. I forgot to run the DM error correction. Let me just run it right now very quickly. It should be very fast. That's why the running error has. Okay, now this is done. This, I guess, should also be done. Okay, this takes some time. We'll just skip it. In here, you can use another useful script called tsview, which is another visualization script in MintPy, and you can use that to plot the point time series so that you can investigate or you can inspect how your data looks like. In this case, if you just click one of them, it will show the displacement time series. You can see in the near the reference point is all 0. Close it is still if you stay on the same fault, on the same side of the fault, it's close to 0. Once we cross the Hayward fault, you can get a 3 millimeter of velocity. And then in here, this is the Santa Clara aquifer. You can have this nonlinear deformation. In here, we are very far away on the mountains on the other side of San Andreas Fault. You can get a linear velocity plus a more scattered deformation because of the tropospheric delays, which is relatively random. And we can estimate, instead of a linear velocity, we can estimate a polynomial with an order of 2 plus a periodic one, basically a sine cosine function. And these are the result looks like. So these are the linear velocities. These are the accelerations from the polynomial. These are the cosine or seasonal deformation, the amplitude of the seasonal deformation, and the phase of the seasonal deformation. We can see that most of the things here are relatively small, except here, the seasonal deformation here is actually bigger, and the seasonal deformation here is also, actually the seasonal component here is also bigger, which is mainly from the tropospheric delays. And the phase of this seasonal behavior is pretty interesting. I remember there's a very interesting paper from Rovina Lochman's group where they showed the usage and the supply of the groundwater in the central California Valley, which really just show us how the groundwater moves in time, which is really cool. So last 4 minutes shows when I want to show this. First, today we have run the small baseline app step by step, which is like the TOPS app, but again also like TOPS app, you can run all of them in one command line without doing those steps. So you can, if you run the options like this, just with your configuration file, it will run all the way through the end without stopping. And the code will do if you update your configuration and you rerun your result, don't worry, still run it again, because the code will do the automatic checking of your input and output and configuration, and will smartly decide if this step needs to be rerun, and it will skip it if it does not need to. So your rerun can be actually fast. Also, is that if you are more familiar, if you're after a while you are more familiar with small baseline app, and you don't like the routine workflow, then you can build your own workflow, because MintPy has many individual scripts. Actually, small baseline app is just a recipe that calls for all those individual scripts that will do all those things for you. So it's more like a toolbox. And if you know what you're doing, you can use all these small utility scripts to build your own workflow and do very customized processing and analysis yourself. The second last one is the parallel processing. It supports the parallel processing using Dask. So if you are doing large areas and you do have a large computer, you can turn on the parallel processing. Usually I have ones that I use. Then I turn on the number of workers into 100, and then I can run it maybe almost like 100 times faster, actually 80 times faster in reality. Then besides the visualization, besides the view and TS view, which we showed today, there are a few more visualization scripts that are listed here. They are useful. Definitely recommend you to check it. And then the last thing, because these ones we already showed that earlier in the course. Last one is there's a recent development that a researcher at GFZ did a plugin called InSAR Explorer, which is a plugin for QGIS. So you can export the MintPy result into QGIS, and then so that you can cross analysis with other data sets. This is a screenshot of that plugin that is developed and supported right now also in MintPy, and there's a script called save explorer.py that will save the MintPy result into the QGIS compatible format. So that's all. Ooh. Let's see if there's some questions.
There is this question at the moment about if you have your own GNSS data, can you import those into MintPy to do a validation? I was just replying to say you could always write your own tool.
Yeah, I definitely will say the same thing. Yeah, write your own code will be very much easier to do that. That GNSS code in MintPy is not really for a deep analysis. It's more for a quick check. You definitely should write your own code if you want to do more in-depth analysis or validation against GNSS. Massive is asking, can we extract the east-west component using MintPy? If so, how? Yes, you can. If you have the ascending and descending, you can use that script that Ravina showed a couple of days ago called the ascending descending to horizontal vertical. But be aware that it has assumptions, because we are in that script. If we are actually using two line of sight vectors to solve for a three-dimensional problem, right? And which is ear post. And so in reality, actually in the code, it's by default is assuming there's no north-south deformation. So if you know that is no north-south deformation, then you do that decomposition, you can get a right east-west component. Otherwise, the estimation is biased, as you can imagine. And also, if you have a fault, and then you know, for example, a structural fault, then you know there's not much horizontal deformation perpendicular to the fault, then you can specify a direction of the horizontal deformation. And then you can decompose your ascending and descending result into vertical and fault parallel deformation. Then that's also a very valid and reasonable decomposition. Okay.
Thank you, Yunjin. I think we need a break, and certainly you do after that.
Yeah. Yeah. Then Scott will take over.
That's right. So 10-minute break. Come back.
I think me and Sarah will be able to squeeze in Opera and Dolphin into an hour.
Then we'll be back on schedule. That would be great. But yes, I think I need to have my lunch. But to lead us through some Opera things.
So since we're 50 minutes behind or so, I think I can make the Opera displacement intro kind of blend smoothly into Dolphin. Probably more people here are interested in, but it could be equal parts. Reason being, Opera was made with Dolphin, so explaining the layers of Opera gives a start of the explanation of what comes out of Dolphin.
Yeah, so to the extent that it explains the relationship would be great, yeah.
Yeah. And also, I mean, Yunjin should go to bed. So I don't think he, like it says Yunjin / me for Opera as loading into MintPy, but I think we can just, like, he can go to bed and I'll show, there's like a command to prep a time series.h5 file from it, because that's basically the output is the time series. And then yes, he explained all the steps that you can do with MintPy.
Yeah, please go ahead. I'm watching and listening and learning.
Okay. Then I'll start. So Sarah is also on the call. She's going to talk some about Dolphin because she had a good example with ISCE2 outputs. So I think a lot of people want to run it with ISCE2. Opera's big project run by JPL. The target of it is federal stakeholders. So it's like they call it the Satellite Needs Working Group, was something that got together and asked different federal agencies, what data products do you want from remote sensing satellites? And what they came up with was a list that you see here. There's surface water extent, so dynamically, where is the water on the land? A surface disturbance, so what's the ground disturbed for anything really, like forest changes, ground changes. And then there's the kind of intermediate products of radiometrically terrain corrected products. And so that's an RTC that you can download and is nice and easy to use, and people like that one. There's what's called this co-registered single look product. So this is a geocoded SLC. It's probably, I guess, the first one you can easily download and work with, but ISAR is going to have a similar one for the full frame. The one for Sentinel looks like the small burst. So a frame may have 27 of these burst products that people are mostly used to working with a full swath, but here you can download individual bursts easily. And that leads into the displacement product, which uses the geocoded SLCs. And what we're working on now is the combined vertical land motion that would basically be, hopefully, the output of something like a careful MintPy analysis that's really like, what is the ground moving? How is the ground moving at this location? Some of the characteristics, this is from my AGU talk last year, is that this displacement product is easy to use relative to other InSAR products. And like, as you've seen, it takes a week to learn the ICE software so that you can start making your own displacement time series. But it's still, I would say, intermediate in that it's line of sight. So every track has a different viewing geometry. It's trying to be pretty high resolution so that you get 30-meter output spacing. So that is still lower resolution than some people want for like TerraSAR X urban analyses, but it's quite a large amount of data for a lot of North America. And it's also trying to be low latency in that every Sentinel acquisition comes out, there's some auxiliary products, and we're trying to get it out within 72 hours. So a few days of when those are available so that you can have a continuously updating displacement time series. And to get I guess the output of it is maybe a third of the way into what Yunjin walks through for the full MintPy workflow, where that one starts with unwrapped interferograms that you need to invert to get a time series. This is an inverted time series that you can download. The caveat being that because we process in batches, the reference time will move forward. And so if you download, say, the first 15, it's a continuous time series. And then the reference time crosses over. And so you need to do a summation to get a full, like, 8 or 9 year time series. But we have tools to do that with Opera. There's a repository called Opera Utils. Do the S1 products use coarse orbits? So the historical processing used the precise orbits, and then everything in forward stream is using the resorb, the restituted orbits. And so people who have done a lot of careful analysis and made interferograms with ionosphere, you'll see sometimes burst to burst phase jumps from that. It's definitely an open area of research to come up with a long track ionospheric correction for geocoded SLCs. Haresh has not come up with that yet. if you download one subset like this, you get something on the left. So this is over West Texas, and the jumpiness I'm showing here is just to show that it's a line of sight displacement, but it's a noise plus displacement. We have not tried to correct for turbulence. There's a separate tropospheric weather model based correction that will be coming out probably in a couple weeks. But it's still pretty useful to get something like this, so that with a simple temporal filter, you can get a pretty clean displacement time series where you're using a well uplift from too much injection over West Texas. The data size is pretty big, and the outputs. So I should mention that this is what the frames look like. So the burst ID map is something that ISCE puts out. We grouped together 27 in a row and have one overlapping burst triplet, so that this doesn't move over time. You don't have to worry about downloading some frame of Opera and then having it shift and having to figure out which one it is. We've actually taken care of looking historically where bursts are missing and just completely excluding half finished data. So whatever you get in one frame, it's going to be continuous and gap free over time. So that was kind of an executive decision by me to throw away some data so that it's a lot easier and you don't have to plot things, figure out what's missing, and then remove stuff later. It uses phase linking that we talked about on Wednesday. So that's the DS processing that fills a lot of the gaps, because the PS processing that we use is the simple amplitude dispersion, because we needed a quick processing technique. We have 4 to 5 quality metrics that we'll look at in a second when we have the example product. Here I'm just showing that this temporal coherence is different than the MintPy temporal coherence. Sorry that the term is overloaded. This is the phase linking temporal coherence. So the idea is the same. It's the misfit from the optimized phases compared to the reconstructed interferograms. So basically, how well do your input interferograms that don't have a full phase closure, how well do they agree with the output phases? The problem with that, it's a very useful technique or quality metric, because it's the same resolution as the output, but we were working with relatively small batches at a time of 15 to 20. And so there's a smaller dynamic range that the temporal coherence shows. So we have another one that the phase cosine similarity metric, which was developed for a paper that was Ann Chen. So her student came up with it for a PS picking, but really it's a general metric to get from interferograms. And so we take our nearest 3 interferograms, take this metric, and it's actually, even though it's a spatially, it's looking for similarity in a neighborhood window, you don't get much of a smearing effect, and it's a pretty high quality metric at 30 meters. The last thing I'll say is that during the processing, we process a nearest 3 network. It is different than the MintPy standard interferograms doing an inversion. After phase linking, you have one continuous time series, and then you simply do differences without extra multi-looking. So there's no more phase misclosure in your interferograms. And you do this because it's easier to unwrap short interferograms even after phase linking. So in some cases, you can just form a single reference network like people do with PS processing. But we found we actually got a lot better results by reforming nearest 3 network, doing an inversion, and then reconstructing that after. But because that we input phase linking results, the residuals from your inversion are basically always going to be either 0 or 2π multiples. There's no more like a Gaussian noise around 0 that you're also inverting for. So because of that, we found that doing the L1 norm minimization got a lot better results. And without doing that, with doing a simple least squares, any single interferogram that's unwrapped incorrectly is going to smear out the outputs, smear out the errors over time. And so this is just saying if you have 30% errors, similar to Yunjin's paper, using the L1 can mean that with some residuals, you still have perfect reconstruction. And so the actual error is 0. So that's the whirlwind processing of how you get to these time series results that are coming from Opera. how do you find them? I think there's 3 ways. I'll actually start with the one I use the least, which is search. So you can go to Opera, dataset Opera S1, filter for the displacement. This gives you the frames. And so you can see here the file name is Opera level 3, Dispass 1. And then this is the frame ID. So it's there's about 45,000 frames globally, but we only have about 1,400 of them over North America. And so you can download individual files. One of the reasons I don't use this is I think I'm trying to work with ASF to get the date filtering right, but it's a CMR limitation that if you want to filter by date, it actually uses the reference and secondary dates, even though we don't particularly care about that. And so if I want just a month of data, I'm looking at the secondary date only. The probably coolest way that I would recommend you poke around that we mentioned before is the displacement portal. So ASF built this. This is kind of like the EGMS portal, but with Opera data. And so you can zoom around and it has all of the processed products that we have so far. In the next week, we're kicking off the final, we labeled them region 1, 2, 3, and 4. And I basically went for the easiest parts first and then worked to gradually harder and harder areas. But you can switch ascending and descending. Here, there's no descending because ISCE has taken about 3 acquisitions total for this area. So we were not able to make a useful displacement product. But ascending has full coverage over here.
Scott, so you start processing next week. What is the rollout date for sort of the Alaska and Washington state kind of data?
Probably end of week. It's because I am going to end up throwing away a lot of data as you get to Alaska. I think I did a recent snow analysis with some like weather historical analysis data, and I basically go from throwing out maybe a month here, more and more up to throwing around 6 months, occasionally throwing around 8 months. That I think it ended up matching Zhonglu's paper very closely, where he did an analysis over a glacier here and used only 4 of the months, and that's about what we kept to. When we tested areas here and kept a lot of data and only threw a couple months, it really degraded the quality and all the coherence metrics were lower, and then we just had very, very crappy results. So this is what we have so far, and you can zoom around. You can see some things right away that are noticeable, like the Ridgecrest earthquake. If you're familiar with the California Central Basin, you'll notice that this looks odd right away. And ASF has a lot of good documentation about that, including the caveats where this portal is showing the short wavelength displacement, which is in order to get a continuous map from frame to frame to frame, where every one of these has a different reference point and different line of sight viewing geometry. We just do a spatial filter so that essentially we're taking a bunch of the tropospheric noise out, but it also affects large scale displacements in space. So it means that even though the full displacement product, if you download them and do a linear fit, it looks like this over California, the portal shows something like this. So local displacements that you zoom into are relatively unaffected. And so you can find things like, oh, look, here's that thing in West Texas where now there's a big well that's coming up. And because this is a small scale uplift, then it's not affected too much by the spatial filtering. And also, so I would recommend checking this out. And oh, apparently this was like a very recent uplift. I hadn't even noticed that before. There's a lot of good documentation. It's cool. You can share this. So you find a cool thing, you send the URL to a friend and it'll take them right here. You can then download this time series. And so it'll export to CSV and then give you that so you can plot it in Excel or Python. If you want to work with the full displacement data, you can either search with this or you can do the Opera Utils library. And there's like I've made a bunch of things for searching, for downloading, and also for streaming the data. Should I take a second to have people? I guess I'll just point out that for this, I'm using this Dolphin M, and so now it's renamed EarthScope Dolphin M.
Yeah, I think it's probably a good idea to encourage people to make a kernel at this point.
Okay, then I'll remind you that you go to this Conda environments, open the create OSL Conda environment notebook, start shift entering through, see what environments you have. So I built this other one before it was renamed, so I have 2 copies of it. As you go down, it'll say, here's the path to the, you can choose a locked or unlocked. So for this one, I'm going to be bold and try an unlocked because it doesn't take too long. But if you want to be stable, you can do the locked. And now you run the next. And so you see, okay, which of these unlocked environments do you want to create? And just make sure. So that one's clicked for the next one. And now this one, you click it. Oh, sorry. We'll do Earth Scope Dolphin Env. And so now with that clicked, you go down and run the next cell. And it'll say, okay, I'm going to make an environment with this location of Earth Scope Dolphin Env.
And if you're like me and you don't have it showing up on your list, it's because you need to restart your server.
That's true. So I'll paste to the chat the scope Dolphin Env. Where is it? Oh, sorry. No, it's OSL environments. Let's see. Maybe one of you can post into the chat where that separate repo that ASF has that lists all of the environments in case you don't want to restart your server and you just want to copy over an environment file.
Yeah, even though restarting, if you have a warmed up server, shouldn't take too long. Okay. And so while you're building the locked versus unlocked, the locked kernels are meant to be a more long-term stable. One of the great things about Python is it's very dynamic and there's lots of new capabilities all the time. But one of the downsides is it's very dynamic, and so libraries change quickly, and there can be compatibility issues creeping in. So the lock kernels lock certain versions of codes, and so it gives you sort of an intermediate term stability of code working, but not long term really, because even locked kernels run into issues when when certain functionalities go away or are not allowed anymore, not supported, etc.
Right. I've pinned very few things, so I would expect in 6 to 12 months that something would change. I will note that for running Dolphin, you can really just install Dolphin, kind of like MintPy, and it includes Opera utils as well. So these other ones, this is just for handling some plotting and streaming, and all the rest is plotting and visualization things. So if I were making a kernel just for running stuff, I wouldn't need any of this except for Dolphin.
Hey, Scott.
Yes.
For the large scale product, how did you do your reference point selection?
The reference point selection is, let's see, do I have it in the diagram? It is chosen as a high coherence. So basically a PS point. It's an automatic selection that is not trying to do any kind of zero deformation selection. It's also not trying to be the same reference point from mini-stack to mini-stack. So that's another caveat, is like the Opera utils handles this when you reformat the data, but you will need to spatially reference it in some way as you combine a long time series. So basically the only things I considered was pick a really high coherence point, so a PS point, and then try and pick it in the middle of the largest connected component.
Gotcha. So it's all relative then. There's not.
Yes.
There's no attempt to make it zero deformation. Gotcha. Thank you.
Yeah, and one benefit of the spatial filtering that's applied in the portal is that it allows us to mosaic all of these tiles that are being created, even though they all have different reference points. So it sort of normalizes the product and leads to a contiguous visualization of the product.
Yes, yeah. When you have a little window that is a sliding window filter that you're moving and subtracting, then basically your reference point is the average of everything there. That's another reason why you see these like red kind of shining boundaries around real subsidence, is that if you can picture doing a moving window around this, the real signal is down, but subtracting the average brings the edges up a little bit. So that's one unfortunate side effect where it's not real uplift here, but it's the visualization artifact. Okay, so this comes down, this should work now, and then now you can activate Earth Scope Env. So we have a DISP subpackage in Opera Utils. You can search by the frame ID, the start and end date. I'm going to skip the other parts for now. How you find the frame ID, one of them is using the search. One of them is clicking here. Whenever you click on a point, it gives you a frame ID. So this is, remember, you have ascending put up here, and that means that in this area it's frame, but it can be a little bit hard to tell like which part of here are you going to get, are you at the edge or anything. So you can search here too. And then here we're going to download a subset of it. So actually the search is just the results. It doesn't download anything yet. So Opera Utils also has built in the functionality to get the S3 URLs. So since we're running on this OpenStar lab, we'll have fast data download access, but we also can now directly access the S3 links. And that means we can stream it in pretty effectively, and it doesn't take super, super long. And so Opera Utils has that HDF5 direct access functionality that people will probably want to start using for NISAR too. So here I'm doing, I'm searching for this frame that I picked out, and I am looking for actually just a 2-week period. We're going to look at the Ridgecrest earthquake. And so this is, if you want to look at basically the equivalent of an unwrapped interferogram, you can get the product before and after and subtract them. So even though there's a reference date much before that, the difference of these two is basically the displacement from July 16th to, relative to July 4th. And that's when the earthquake happened. So here I have this open file that remotely opens a file from a URL. And so even though we haven't downloaded anything, we can run this. Well, that ran a lot faster the second time. I'm going to restart this actually. So one thing that this open file does is it will search for your credentials. So assuming you have the netrc file set up correctly for all the other downloads you're going to do, then it is somewhat tricky to actually access this from S3 on an EC2 instance because you need these temporary credentials. And there's other libraries that handle this, like the Earth Access library, but I've taken the core functionality of it. And so now you can open file in a few seconds. And so you see all of the layers inside of it. We're going to look at, we'll plot these in a second, but it's the displacement is the full wavelength displacement as compared to the short wavelength displacement. And so we can now open a second one and subtract the secondary minus the reference displacement. And that's going to run, but this is what it will look like. So this is what the frame looks like. And this was the Ridgecrest earthquake. We can subset it based on a few different ways. So this is using X-array syntax. I'm going to skip over it for now since we're short on time, but we can zoom in to the fault rupture itself. And so one other note about the processing is that to speed along unwrapping, we've used Snafu for basically everything. We had a few options that are available in Dolphin for unwrapping that we tested a lot. We settled on Snafu, and we settled on Snafu's tiling mechanism. So we actually, Snafu has a built-in way to tile so that it speeds up interferograms and then it tries to reassemble after. So basically, this is like the biggest earthquake that's going to be available in the North America area. And so it's probably the most challenging for a single unwrapping. We don't actually expect people to use this instead of like earthquake groups to form their own, because that is like their specialty. But it can be useful to see what quality metrics say about this product.
Even for earthquake specialists, unwrapping that thing is a nightmare.
Yeah, exactly. So it's not the fact that there's not obvious tiling artifacts, I think would surprise people, because a lot of people are resistant to Snafu's tiling since they thought like we didn't do anything to like center around this. We just do 5x5 tiling. So there's certainly some kind of tile that crosses over the boundary. The quality metrics that are in here, one of them is, two are the temporal coherence and phase similarity that we mentioned. There's an estimated phase quality that we actually use for the purposes of unwrapping, because phase linking doesn't give you a normal interferometric coherence. You've made all interferograms, so you had n times n-1/2 coherences, and now the output is just a vector of n. So there's really not an equivalent thing that you would feed to Snafu. So what we did is just kind of a moving window of the phase, and it gives you something that's 0 to 1. It looks similar in some ways, but it's blurrier. It's not my favorite. Actually, it's my least favorite of these four. And then there's the time series inversion residuals that are from the nearest 3 unwrapping the L1 inversion. We've kept it in radians so that you can see when there's 0, and most of the pixels should be about 6.28 or 12 point something for 4 pi. So you can actually see here I'm doing masking only pixels that aren't exactly or roughly multiples of 2 pi, because that's the largest sign that something went wrong. When it can't find exact multiples of 2 pi, then all of the interferograms didn't agree with each other. And so here I'm also subsetting on the temporal coherence and finding things that looked okay in the inversion residuals, and we end up with this. And so that actually looks a bunch better and doesn't have as obvious of artifacts in here. But this is just to give you an idea of how you might manually mask data based on your study area, and if you want to be stricter or looser.
We have a very burning question in the Q&A, which is, why is it called Dolphin?
Why is it called Dolphin?
Yeah.
I'm not even going to acknowledge that. I don't agree with the NASA policy of naming everything by acronyms. I don't think an acronym makes it easier to understand. I don't have a reason. I think I came up with an acronym because somebody, like 5 people asked me that, like, what does Dolphin stand for? And I was like, it's deformation online phase linking interference. I think it's in the README somewhere. It's like yeah, I think there's an Easter egg where I've commented out a possible backronym for it, but don't.
You just like marine life.
I just like dolphins, and oh, here we go. Deformation land surface products in high resolution using InSAR, if you want that. Yeah, I wanted something short to type, and I like things that are just easy to say, and dolphins are cool. So here are the layers that are in a product. We have a recommended mask, which is, for a lot of it, it's actually a very loose mask, and you may and or probably want to mask a little bit stricter. So we went back and forth on whether we should be super strict and show little, or be generous and have people mask it more, but we ended towards the looser end. There are connected component labels, and this is probably the most confusing for people like Yoonjun, who know what they are in depth and now have seen it after an inversion. You can actually take Snafu and run it on an unwrapped interferogram with something like a correlation, and it'll produce and run just the connected component part. That's a part of Snafu Pi, which is what we use, where you can request. So I guess this is also a plug for it. Jeff Gunter wrote this nice wrapper in Python. So you can call on a wrap on something, and you can also call, it's not shown here, but you can call build connected component labels. And so that's what we did for this.
That sounds like a really useful thing for people using hype.
Yes, exactly. I lost it because the Zoom chat is really weird. But the person who asked, in Gamma, we don't get this. How can we use it for MintPy? You can take SnafuPy and run it on your unwrapped phase and get connecting component labels for pretty cheap.
That's great. Actually, we should talk to the ASF team to integrate that as a feature. For folks that click on ASF has this MintPy, prepare for MintPy option, and it could just run this additional script.
Yes, if you can't find it in there, I'll send it. It's in the DisPes1 repo, like the actual production code. Okay, so we can, I guess the thing I'll say about this is that this is why I don't like estimated phase quality, is that the blurring of it, when there's very high density fringes, then it looks like it's low quality, even when these, if you plot the interferogram, it's actually very pretty fringes that are coherent. And that's a little bit affected with the phase similarity as well, but not nearly as much. And so this is what you would look like in the portal, is that it's closer, but it's a little strange looking if you're used to the full wavelength interferograms. And last, there's a corrections group. There's only a couple corrections. So we included PySolid. So you can just take this layer that's in /correction/solid earth tide and subtract it. We have an ionospheric delay that's really the range delay only. So it's a very long wavelength correction. It's made from GPS modeling of the total electron layer content from the GPS network. So it's somewhat accurate. It's sometimes a little bit off. If you're looking at a small area, you don't need this. And we have the perpendicular baseline for, that's an image, so it's the same size if you want to attempt to correct the DEM error. So this can be used to plug into MintPy, the DEM error correction. So that's one product. And for this one, we'll show how we can extract a time series and actually prepare a stack file on your notebook or on your local machine. So similar to the search, Opera Utils has a DisPes1 download. You can specify the directory that you want, the frame ID, and similar frame ID, bounding box, start and end date. This can only work on an EC2 instance that's in region, is what they say. So it's next to the data on AWS. So it runs a bunch faster. And then this is how many parallel download threads you want. So when I ran this, I found 120 dates for this subset. It downloaded it in about 10 minutes. And they all look like this. So they have the reference date and secondary date. This third one is when it was generated, but these are the important. So this is from November of 2019 to January of 2020 is what this product has. And you see it change over here. And so to handle these reference changeovers, we can run the reformat. And so there's a couple of different referencing options, which you can see here. I think some people aren't a fan of the distributed reference method that I know Rowena uses. So there is a point if you want to select a lat long point. This S1 reformat. So it can also output in a ZAR format if you like ZAR. I think ISCE is starting to do more and more in ZAR. There's other options that we won't go through at the moment, but yeah, the reference method is you can select a point where you say either the row call or the lat long. You can also, if you do just a small area, say around like a subsidence bowl or an uplift bowl, you can say just reference by the median of all the border pixels and then assume that the border is averaged of 0 deformation. Or you can do the whole scene median, or you can do pick out the highest coherence points and do the median, which is something that Howard Zepker's auto processor likes to do as well. And so this runs for something that's a small subset. It just takes a few minutes to set up your stack file. And one caveat is that I did this for an output of netcdf format. And so to make this run quicker, I actually am it's called a virtual data set, and it links to the existing Opera products that you downloaded to save some disk space. if you do the ZAR, it'll copy. If you can also have an option to copy everything if you don't care about duplicating disk space. But once you have that, then you have now a data set that's 120 times and only 700 by 1200 pixels. So you got this targeted deformation time series that's continuous in time, and you got it in under 15 minutes. And so you can plot the last displacement. So this is the cumulative one, and it looks something like this. If you can see, there's some noise, and this is based on that loose recommended mask let it talk. So if you want a stricter threshold, you can build that up either with X-ray or with MintPy. MintPy is fine at handling
the San
HDF
Andreas port.
This is,
yeah, the creeping segment.
Yes, yeah, I picked one that was there and has a little bit of Central Valley, and it's also, I think, got some
landslides,
creep-induced landslides. Yeah.
I like the landslide piece.
Yeah.
Something
okay. So
for everyone.
So yeah, and I guess I'll actually skip this because this is kind of general Python reprojecting, plotting. You can do this with MintPy. And then I'll skip to the bottom. So to prepare for MintPy, soon the opera utils will have these static layers available on ASF. They haven't been produced yet, so I manually copied some up to our bucket. And they are the same size as the frame, which is 7,000 by 9,000 pixels-ish. And so I did this is how you would copy down and get a subset. And this one is then a module in Opera Utils to prepare a MintPy set of files. So once you run this on that stack file, then you give it a sample displacement product to give the rest of the information on the geometry and other things that it needs. You point to where these geometry files are, and then it gives you this output in here. So then what we get out is the geometry geo. The time series is the main displacement layer. So that's kind of what Opera has produced. And now it's just put the metadata in so MintPy can recognize it. It makes an average velocity while it's happening. This is something the Opera science team started to use, is rather than like have a mask at every epoch and then have it propagate for all time, they would look globally at which pixels are masked, and if it's masked more than 10% of the time, then they would mask it entirely. And so this is how often a pixel is on or off. And then it averages one of the coherences to get that. So this is very like new and fresh. And if you are more experienced with MintPy and want to translate some of these, please feel free to. Some of these don't have like direct other analogs in MintPy right now. So there's plenty of opportunity to translate more from the Opera products. And this was just demonstrating that once you have this, you can do a view.py and get the full time series out like this. I guess one last thing I'll say about what we did for debugging a lot of the time. So this is valid for Opera and for Dolphin. This is like not a very well publicized thing yet, but we have a browser that I called Bowser, just to confuse people. And I did this. This is less for making publication quality plots right now, unless we get more money to work on it, and more for debugging a lot of data that can be like tens of gigabytes and just poking through it very quickly. So this is that area that results from here. This is the MintPy time series file. So it, I guess I'll plug another thing that if somebody wants to be adventurous and revisit a 2-year-old pull request that I made, I added something so that you can just add the X and Y data sets and netcdf convention metadata. And then that makes a time series H5 file recognizable by GDAL. And so this uses GDAL to plot it on a geographic map with the rest of the map tiles. And so once you have this, you can zoom around and it dynamically tiles things for you. So it makes it higher resolution when you do in, and you can click on things and it'll plot the time series. You can slide it away and see, okay, that did look like a time series thing, and there's more. Yeah, looks like landslides. Yes, we found this useful, but I know that you've already had 5 different visualization tools thrown at you, so I will let people explore things as they need.
Yunjun has his hand up.
Yes.
I got really nice results and tools. I'm actually wondering, in the end, when you load the things into MintPy format, the masking and the time series density, do you mean that are you guys using this to handling those temporarily coherent scatters disappear and reappear as coherent in time?
Yeah,
What's
that
the
was
what was the motivation for this?
the motivation was that the recommended mask is made at like groups of 15 when we process historically. Some of them, like basically over Hawaii, there'd be a drop in temporal coherence or similarity for the 2018 eruption, and then it looks fine after. Or just in other like vegetated areas, it'd be like 1 or 2 mini stacks where it drops down and then it comes back up for most of it. And so they want to see more pixels. And so rather than have like a step through time that at any point a pixel disappears, then you say it disappears forever. Grace and Simran did a lot of work to figure out like how to look at the entire time series of masked and not masked, and then just make one mask. So I would say it's pretty arbitrary, and if it doesn't make sense, then I would change it.
I'm wondering then with if there's an eruption or earthquake happening in the beginning, and then, as you said, then how you interpret the cumulative deformation if there's a there's a gap in between.
Yeah, you have to make an assumption that is one thing that's on the portal right now. Is, well, this is an actual gap, but one thing that we have, which I guess not everyone agreed with, was for like a single mini stack of 15 dates, if they disappear, we have just open dots. And so that's like, we are assuming nothing, but we're assuming the ground did nothing during that time. And then we just pick back up the time series after that.
See, thank you.
So there's that. One of the options for this was to propagate the nans or not. Sorry. That's, yeah. You're right that there is an assumption that you have to make. And so you can do a conservative one or a easier one. That's another reason why we didn't see it as like a terrible deal breaker to have this moving reference date, is that if there's something that happens early and it would like break coherence, you may still want to look at the 8 years of data after that. And
right. Yeah. It's a very difficult question in itself.
Yes.
Yeah. Interesting.
But yeah, this one you can switch between the layers when you have all of them. This is from an output of no, this is a displacement stack. So this works with Dolphin too. So here's the blurrier one. Here's the temporal coherence. Here's the phase similarity. And here's the displacement. So you can flip through it, see how it changes.
Blue is in this sign convention is subsidence or movement away.
Yes, exactly.
Okay.
I think it might even be in. Let's see. Yeah, okay. Description, line of sight, positive values indicate apparent motion towards the platform.
Awesome. I love people who document their sign conventions.
Yeah. Okay, so that's Opera. That's how we got it. And I think to fit it in, we'll start talking about Dolphin now. Is Sarah still here?
Yes, I'm here.
Okay. Yeah. So to give a preview, this was the New Orleans area that we have two versions of it processed, one with ISCE2, one with the pre-made co-registered SLCs. And so Sarah's first going to show the ISCE2 version.
Okay. Am I able to share?
Yeah, you should be. I don't know if you see there's a green up arrow button on the bottom of your screen.
Okay. I guess I have to
leave and restart.
log off. Yes.
Yeah, that's a typical Mac problem.
I'll watch for you.
Any questions while we wait? Scott?
You might want to say why you might want to do all what you can do in MintPy once you have all this this linkage between the two softwares.
True. So describe where it fits in. Dolphin needs a or Opera. It took in co-registered SLCs already. The output is the displacement plus noise. And the Opera data has just a couple of the corrections you might want. So it has the ionosphere of like a very, if you want to do very long wavelength corrections, or it has the solid earth tide that has the cyclical corrections. But then all of the, so Yunjin I think listed 10 or 12 of them. And to do correct for turbulence, correct for stratified atmosphere, correct for do analysis of, well, I guess the closure phase wouldn't work, but basically a lot of the plotting, a lot of the further DEM error corrections, those are all possible with MintPy, and Sarah's done it. She has a lot more MintPy experience than me. And yeah, that's, so Dolphin kind of starts, or Dolphin kicks off where the first step of MintPy's workflow ended, of just the inversion to get one time series.h5 file.
Cool. Sarah, I don't know if you mean to be showing us your calendar.
Oh, is it so? Okay, sorry. I thought it's in this slide. Okay, no problem. Are you seeing my notebook?
We can see your notebook.
Okay. So yeah, I'm gonna talk about Dolphin, which is the core software for these cool Opera displacement products that Scott just showed you. So Scott is the lead developer of the software, and if you wanna check that on GitHub, you can check on ICE framework. You can easily install it with Conda or pip, and here you can see the different unwrappers that are used in this software, and you can set any of them for your own process. So how we can generate those cool displacement maps? If you want to run this notebook, it's just a setup at the first cell. I'm not gonna run it because it's taking so long. This New Orleans data, this is processed with ISCE2 TOPS stack processor, and it has co-registered SLCs, which are the inputs to Dolphin. Dolphin can process both in geo-coordinates or radar coordinates. I'm showing in radar coordinates, and later you will see a demo of GSLCs that Scott is going to show. So when you download the data and uncompress it, starting with Dolphin, you saw this flowchart earlier. It will start with co-registered SLCs. Dolphin does an analysis on PS selection, which is based on amplitude dispersion, and then performs phase linking on the distributed scatterers, finding statistically homogeneous pixels for each pixel, and then making that coherence matrix, doing the optimization to get the wrapped phase series, and then performs unwrapping with different techniques that you would select. And then it does a time series inversion, produces an average velocity and displacement time series. If you want to start with the software, the help shows 5 subcommands. The first and most important one is the config subcommand. If you just run Dolphin config print empty, it will create a YAML file which contains all of the config parameters that you can set, or you can simply give the direction to your data in any GDAL compatible format that you have, and it can read it. I'm showing just first 60 lines of this config. And there is also a complete one here. You can check later different parameters that you can set. I want to say there are some of the main parameters that you have to consider when you're processing. First one, you have to give it a CSLC or GSLC list, and then if you set the wavelengths, the time series and the output time series would be in meter units, but if you don't, it will be in radians. Strides is the output is what creates the output resolution. It means like if you set 3 as X, it will skip every 3 pixel. And half window is what you basically select for the moving window to find SHPs. And then in interferogram network, which is, let me find.
Lower down.
Okay, sorry. Yeah, here. There are 2 options, main options. Reference index selects the index of your single reference network reference index. So if you don't select it, then with the max bandwidth you can say to generate, for example, 3 nearest neighbor interferograms for unwrapping. And then in the unwrap options, you see all the options, and for each one of these libraries, you can set different config parameters based on your own application. Yeah, so when you set your config, then you can run Dolphin, and it will do all the process from 0 to 100 without doing anything. For this data set that I have here, and you can try later, it will take almost 3 hours on OSL. And the final velocity map that is created is shown here. I just want to show that there are 3 other subcommands. If you have a set of interferograms, you can unwrap it with this command. If you have a set of unwrapped interferograms, you can invert for time series. And if you want to generate the short wavelengths displacement maps that Scott just showed, you can use the filter subcommand. And this is pretty much all the steps from Dolphin, which is really easy. And I will hand to Scott to show the GSLCs for you.
It was a great time. I guess maybe I'll we're wrapping up pretty quickly, so my notebook is not too different than Sarah's. Trying to think if there's anything else I want to speak on. In this one, we use Opera Utils again to search, download. One note about using the burst SLCs. It's like a common annoyance to have the shifting granules from ISCE, and so then sometimes you get data and it's missing, or you download more than you need to cover everything. There's this option where it will look at the whole time series of SLCs you might get, and if you have, say, just a part missing from one date, and that's the only part, it'll ignore that date and then make sure that you have a continuous set. So we use this for the Opera processing to make sure that we had the same spatial coverage every single time.
Scott, maybe you want to explain more on the Opera C SLC and what the students they think they can use for their own.
Yeah, let's see. So I'm not sure if I have a good, the CSLC, maybe I'll do a search on this. So if we search here, you can search, this one is useful on ASF search. So you can go level 2 co-registered SLC. And so here, you can see where these are coded, and these are both ascending and descending together. So to make it a little easier to see, we'll filter for just ascending. And these are now 2 different tracks, which I can only tell from there. Oh no, so it's one track. That they have the name that tells you which track it is, so the relative orbit. This number is from ISCE. They've labeled them from like 1 to 1 million-ish. And then IW123 is the subswath. And so, so it is 2 tracks, yeah. So for this area, you would download just say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 instead of 30 or 33 for each frame. So it's a nice way to get a subset of a full frame. The difference between this and the ASF bursts are that the ASF has a similar burst mapping to download much less data. Those come in radar coordinates. So it takes, in some way, you have to stitch them afterwards. Whereas these are also different, but these are different spatially. And so you'd process them separately for phase linking and PS processing. But Dolphin, because we made it for Opera, Dolphin is aware of how to stitch together the geocoded SLCs so that you can just download a bunch of these and you'll come out with one continuous map. And so that's what we did for this area is we looked for a polygon of interest. And then because I knew what I wanted, I picked 2 different burst IDs. So there'll be 2 different separate stacks processed. And this explains more about the naming of the CSLCs. So you can see the date and the burst ID and where they are from. The extra option that you'll need to use for Dolphin is that these are HDF5 files. So there's a sub data set is what GDAL calls it. So one, I think MintPy just calls it data set. Other people call it data set. Inside the actual complex data is located here. So you just need to specify where that is. I should have mentioned the strides earlier. So I said that Opera is 30-meter posting. The inputs are SLCs that are close to full resolution. They could be sampled higher if you wanted to get really like no aliasing at all. So 5 by 10 go to 30 by 30 means we process and skip, we decimate by 6 and 3. And so although this PS processing, there's a regridding operation. So if you really care about fine resolution PS, you wouldn't do the strides. You'd want it at the same output posting as input posting. But if you want something at 30 meters or even 50 or 60 meters, specifying the strides will be an approximate linear speed up. So that's one thing. I don't know, Yunjin, are you using MyApplePie still?
Yes.
That's probably like the largest speed up difference for Dolphin, besides like the using JAX for the compiled Python code. That for this you can specify strides and it'll run 18 times faster.
Right.
And for the separate geocoded SLCs, you can say I want to process 2 bursts at a time because each one is actually pretty low CPU usage. So if you have 8 cores on your machine, you can specify 4 parallel bursts pretty easily. And for one big, like ISCE2 raster or an ISAR, this will process extra blocks at a time. So it does still increase the parallelism. And yeah, last you can actually subset the bounds. So these are pretty small relative to a giant frame, but they're pretty big when you consider that it's 5,000 pixels by 20,000 pixels. So if you just want really like this area, you can specify that and you'll download the full data, but then Dolphin will skip the rest of the outputs. And so that's what we did here. We specified the bounds. And so for each of the bursts, it'll only process within those bounds. most of the configuration that Sarah showed is in unwrapping options. And if we have time, I'll talk about them briefly at the end, but I think we're running out of time. And so this is another one where we end up with a result because we picked these bounds. We actually picked a pretty bad area to process. So this is right in the New Orleans area. This is a case where the Dolphin output here is actually going to be worse than the Opera output that had the full frame. And that's just what happens if you process an area that's on two sides of a river is you get this. So another option to try in MintPy is put this in and try and use the bridging. We had some mixed results for the automated processing for bridging, and that sometimes it does work, like we know it does. And then Sarah was actually trying this, and sometimes it would make it worse, possibly because this is like two halves, so it's not one little island. I don't know. Maybe Yunjin has ideas.
Scott, there's a question in the chat about where this notebook lives.
Let's see. 5.3. So in the 5.3, the last one, there's Opera CSLCs, and then there's ISCE2. So this is the Opera CSLCs.
Is this pushed to the main repo? I'm not sure I'm seeing it.
Yeah,
I just
no. Yeah, okay.
it's in the main repo. I can see it.
I can see it now. Yeah, sorry.
Yeah, I have it. So
thanks.
Okay. But yeah, Dolphin, as Sarah said, any GDAL compatible SLCs can work. I think I have a branch where I do a demo on hype results, and somebody sent me a gamma stack and it did work, but I think for gamma you have to do something to remove the flat earth fringes. But once you do that, it should work fine. Yeah, are there any questions now?
Oh, I have to go and play with this.
I have a question. I see in the earlier when Sarah showed the steps of Dolphin, in the round part, is that for the face linking or?
The run part does.
That is the whole part.
Run, yeah. You configure everything, and then it does. There are, I guess.
I see. Oh.
So
and
actually,
it never crashes.
Yeah, that's in alphabetical order. There's a sample configuration on here too. But yeah, so there's like general masking options, worker settings you can do, output options to decimate or strip bounds or compress or add overviews, because the outputs in general are GeoTIFFs. So that's why we can reformat them to HDF5. But because we did so much Geo SLC processing, it was useful to have them in GeoTIFF so you could drag them into QGIS. But then there's options for each of the parts of the PS, where the main thing is just what amplitude dispersion threshold do you want. Skipping these extra pre-made files is phase linking options of a little bit more. So how big a mini stack, how big a search window do you want to multi-look? This controls the multi-looking, so larger is more multi-looking pixels. This one is the method that we use to find the pixels, but I wouldn't change it at this point because it's fine and it runs fast. Something that's new, and we're out of time, so I don't have time to explain it, even if I fully had it prepared yet. But we actually have an estimate of the phase standard deviation based on the Kramer-Rao lower bound formula for phase linking. So this gives you a wrapped phase standard deviation. I just added a thing since we formed the covariance matrix of all interferograms, we occasionally want to see what does the nearest neighbor sequential phase output. And so here, if you turn this on, which is off by default, you can get a set of rasters that are the every 1, 2, 3 loop of wrapped closure phase. And Sarah talked about the network. and then the other half are the unwrapping options, because we have 5 that are available. Snafu is the one that we know, which uses the Snafu Pi wrapper. I guess the last thing I'll say is because Piyush put a lot of effort into this. There's a 3D unwrapping option. This is something that Descartes Labs, which is now part of Earth Daily Analytics, developed for their internal big data InSAR processor, and then they worked with Opera to actually open source a portion of it. And so this does the extended minimum cost flow and implementation of it. And because it's a little bit underspecified in the paper, it's their take on it. And so it's the documentation doesn't fully explain it, but it's this Pepe and Linari 2006 paper. And basically, if you want a quick mental model of 3D unwrapping, it just does a similar unwrapping error correction to what MintPy has, but it does it in the wrapped domain before spatially unwrapping. And that's the benefit of the 3D.
And it does not assume a time deformation model?
No.
In this 3D unwrapping.
Let's see, did I add my... I didn't. I should merge in. I have my own just play notebook to help understand what the heck the 3D unwrapping is doing. But it really is just every edge. So one pixel to the next, it unwraps the pixel to pixel gradient independently in time, and it just says, okay, it forms nearest neighbor 3. That's the only option right now to make sure it's a planar graph, and it says if there's a plus or minus 1 residue, that means some of the interferograms don't work in time. And so we're going to add something to the interferogram that doesn't agree. And then we do that at every edge. And then we just normally do spatial unwrapping.
Okay. One last question. So for the Opera C SoCs, I see you guys have the code. One is the compass, the other is the suite. Which one are you using which one are we supposed to use to generate these CSRCs?
So this is Compass. So there's 2 related repos because there's so much overlap for the algorithm team that the operated ADT has a bunch of repos in there. It was started by Haresh, the algorithm lead for a while. Compass was made by Virginia and Songsu on here. I don't know where he is. And then I don't know where Yunjin was working on Compass too.
Yeah.
And this is what's running in production because it was designed to just fit in with the Opera data system. It's not the most direct to use. And so while it was getting going in production, we didn't have any. I started suites. This was just trying to do something like the Sentinel Stack app or the ICE stack, where you specify a bounding box, a start and end date, a track, and then it kicks off and gives you unwrapped interferograms in the end. I have not worked on it in a while, except for people kind of pinging me. Something that's close, and I thought I was going to get a demo yesterday, but didn't have time, was that I have used Forest stack to burst processor, where you get the ASF bursts, and then you can run that with ICE3 to get geocoded bursts, and then form interferograms, which is the easy part.
Based using suites.
Yeah.
Okay.
Yeah, so it just is an attempting to be a wrapper around Compass. So there's a geocoding thing.
Yeah, because the compass right now is looks to me like Dolphin. All the configuration are through the YAML files, and if people want to do it in a more automatic or simple way, you don't have the options that you don't have the easy options in the command line yet. Right?
Yeah, exactly. That's was the main reason I did it, is just to make it easier on myself and Sarah.
Okay.
Just,
okay, I see.
I was mentioning one thing more. It's that if you run the workflow, it will go from the beginning to the end, producing the time series and velocity. And if you stop or your process is stopped at any step, it will continue from that part.
That's true. That, yeah, for Dolphin, if you get halfway through and then want to delete the unwrapped folder, then it'll skip all the phase linking and then go to unwrapping.
See, great. As I'm ready to explore S3.
So there are a few questions in the chat that maybe Scott can address without speaking, because we need to wrap up the
Okay. Yeah. Oh yeah. You start the. You can do the wrap up.
Franz, you're there too.
Yeah. So I want to first, thank all the speakers and presenters for all the time they put in the availability throughout the week. So hopefully you enjoyed the sessions. There's we did a lot of things differently this year, not just from the Moodle platform, but also there's new content that we built in this year and tried for the first time. And a lot of this will change also to the next run with NISAR data becoming available. So stay tuned for that. I want to thank Melissa and the entire Earthscope team for coordination, for bringing all the videos to you, for reminding us and all of you, for providing Slack and all of the support services that they've provided throughout the week. This could not happen at all without the continued support that Earthscope has been providing. So consider working with Earthscope more in the future. Also, Earthscope needs everybody's support. So, praise them in all of your future conversations. And then lastly, also the Open Science Lab team from ASF, thank you for, letting us use the platform and for providing support with everybody's sign-ins and issues with the platform. And then lastly, of course, to all of you guys for the participation, for the contributions throughout the week. And we hope you took something away from the course and learned something, and you had some fun doing it. Gareth.
Yeah. When we see you in person, or if you see us in person at conferences, do come up and say hi. It's always interesting to meet the people who behind the names, behind the black rectangles on the Zoom screen, and almost every conference I go to these days, internationally or in AGU, there's always someone there who lets me know that they know me better than I know them, and that's always great.
And maybe thanks to Gareth, because Gareth really carried the lion's share of the office hours and the leadership. So thank you for all the time you put into it and for making this work.
It's always very rewarding to do this, so I am happy to have done it. So it falls on me to tell you what you have to do to finish the course, and I will show you now a couple of things. So we have homeworks for today. They're related to running MintPy. So you want to go off and run the MintPy thing and change some things. So it's laid out here that you want to change the reference point and provide a justification for why you changed the reference point. Apply a tropospheric correction, and if you want to apply the ERA5 troposphere correction, you will need to register for an account with ECMWF and change some things on the system. Some of the other corrections might be easier to apply in that respect. Apply a solid earth tides correction. Okay. And then for the second homework, in the part where you fit a velocity, you have a choice of the different functions that you use to fit the time series to allow you to estimate a velocity. And so try a different one, or more than one different one, and see what it does to your velocity estimate. Save those outputs as PDFs like you've been doing for other things and upload them to Moodle. All right, and then what else have we got? I spent some time yesterday trying to write some instructions on how you might install the course environment on your own machine. I'm very interested to hear how people get on doing this, but anyway, it's posted up on GitHub in the repository with all the notebooks. If you restart your servers, it will download to your environment too. A bunch of instructions, including where to get the Jupyter notebooks. Of course, they come from the repository. How to install the environments that we have used in the course. So the EarthScope InSAR one, AutoRift, and also what was shown today, EarthScope Dolphin. I highlight here that it's an optional step, but basically not really, that you want to edit these environment files a little to include Jupyter as a package to install. Otherwise, you won't be able to run the Jupyter notebooks in Jupyter, although that's a pretty easy thing to fix. If you didn't end up installing Jupyter, you just type conda install Jupyter and it will install. But yes, we have instructions for you. Go off and study at your leisure. There's a couple more things. One is that the EarthScope staff were working today to put together a post-course evaluation survey. There is also a post-course assessment based on very similar questions to the ones we asked at the start of the course about your understanding of InSAR concepts. So please go and complete both of those. They are both linked on Moodle. The post-course evaluation survey is linked here as well in the syllabus document. OSL is going to be kept live for a week. And the reason for that is that we do not have the budget to keep it running longer than one more week. Every day that it is being used costs EarthScope money, and they have a finite budget for this course. So please get everything done as soon as you can and shut down your servers, and you will save us money. Finally, we issue credit for the course in the form of course credit for people who are registered for that, and certificates for people who would like them. If you're interested in getting a certificate, you need to do 70% of the homework, which turns out to be 7 of the 9 homeworks, and all of the surveys, the 2 post-course surveys, and you have to have already done the pre-course survey. And we would like that done by the end of next week so that we can wrap this up and move on with our lives and distribute all the materials to you guys. If you signed up for course credit, you have to complete every single thing in the course. Otherwise, you have not completed the course. Any questions about that?
It's not just we want to move on with our lives, you also want to move on with yours.
Everybody wants to start processing data on their own, right? That's really the goal here. I want to play with Dolphin. I don't know if I'll have much more time. I have a few more weeks before classes start here. Maybe I'll get to play a bit. If there are no more questions, then I think it is time to let you all go. Thanks everybody for coming. I echo everything that Franz said about thanks to everybody involved. And stay in touch. The Slack will be open for a while. We may be able to drop in and help on things.
Yeah, and find us at AGU, IGARS, GSA, all those typical conferences.
Maybe a Fringe conference one day.
Maybe Fringe.
Yeah, NISAR conference one day.
Well, NISAR conference. Exactly.
Oh, that's right. Yes.
Good to see you all. Have a
Bye,
good week.
everyone.